Hi everyone, welcome to Go Classes. In this lecture, we will continue our discussion on interrupts. So this is interrupt part 2. You can find the part 1 on the YouTube channel. On the YouTube, you can search Go Classes interrupt. So this you can search on the YouTube and you can find this interrupt and interrupt processing part 1. Okay, so this lecture you can find on the YouTube. Just search it. Now, what we have seen, let's do the recap. Okay, let's quickly see what are the concepts we have seen in the part 1. So I will quickly tell you the recap of all the concepts. First, we have seen the definition of interrupt. What is interrupt? Interrupt is a signal, or I can say interrupt is a mechanism using which IO devices can send signal to the CPU that they need attention. Okay, software or hardware, both the devices, basically software, hardware, they can send interrupt signal to the CPU and they can ask for attention. Okay, so very simple. Interrupts are signals which are sent to processor to indicate that some event or some IO device needs immediate attention. Okay, so very simple point. Now we have seen what is interrupt service routine. So whenever some interrupt will come to the CPU, then the CPU will service that interrupt. Yes or no? So to service any interrupt, what the CPU will do? CPU will execute this code, this program CPU will execute, that is called interrupt service routine. So remember ISR, that is interrupt service routine, or you can call it interrupt handler. Another name is interrupt handler, or you can call it interrupt service subroutine, ISS. So all these are same concept, different names. But remember, what is ISR? This is a program which CPU will execute when some interrupt will come. Okay, so whenever some IO device will send interrupt to the CPU, then CPU will run a program to service that interrupt. So that program to service that interrupt, this program is called interrupt handler, or you can say this is your ISR. Okay, so remember ISR, this is a special program that gets executed whenever some interrupt signal will come. Okay, and remember this ISR, this is different for different interrupts. So for different IO devices, this ISR will be different. Okay, if the interrupt is coming from mouse, then mouse interrupt service routine will be executed. Okay, if the interrupt is coming from keyboard, then keyboard ISR will be executed. If the interrupt is coming from battery, then battery ISR will be executed. So this ISR, this is different for different interrupts. Okay, for different type of interrupt, this ISR, this program will be different. So very simple, what is ISR? This is the program which CPU will execute whenever some interrupt will come. Okay, and basically to service any interrupt, this program will be executed by the CPU. And one more thing, this ISR, interrupt service routine, this ISR for different interrupt, this is different and this is present in the memory. Okay, for all the IO devices, or I can say for all type of interrupt, we have different ISR, we have different program which CPU will execute. And these ISR, okay, all these ISR for different interrupt, they are present in the main memory. Okay, they are already present in the main memory. So very simple point. So you can see ISR is already resident in the main memory. And remember ISR, this is just a program to service any interrupt. So this is executed by the CPU just like a normal program. Okay, very simple. Now let's move on. Now we have seen what is interrupt vector. Interrupt vector, or you can say interrupt number, and what is interrupt vector table. This concept we have seen. Basically, what is the idea? See, whenever some IO device will send interrupt to the CPU, then how the CPU will find out which IO device is sending the interrupt. Also, how the CPU will find out what is the address of the interrupt service routine. Yes or no? See, very simple point. If any IO device, like for example mouse or keyboard, is sending interrupt to the CPU, then CPU need to find out who is sending the interrupt. Okay, yes or no? Because depending on the IO device, the CPU will execute ISR. ISR for different IO devices, that is different. Okay, so basically there are two questions. The first question is, whenever some interrupt is coming to the CPU, then how the CPU will find out which IO device has sent the interrupt. Also, how the CPU will find out the address of interrupt service routine. So these are the two questions. Okay, so let me tell you, this interrupt vector, or I can say this interrupt number, this is used to find out which IO device has sent the interrupt signal. Also, this interrupt vector table, this is used to find out what is the address of interrupt service routine for any interrupt. Okay, so very simple point. Let me tell you that you have a CPU and this CPU has two pins. Let me tell you that these are physical pins, these are hardware pins. So CPU has two pins. One is interrupt request pin, another is interrupt acknowledgement pin. Okay, so on this interrupt request pin, what will happen? Any IO device can send interrupt request signal. Okay, and this CPU, what it will do, it will send the interrupt acknowledgement signal to the IO device. So every CPU basically what it has a single interrupt request pin, also it has a single interrupt acknowledgement pin. Okay, from the IO devices the interrupt request will come on this pin to the CPU, and from the CPU this acknowledgement will go to the IO device. Okay, so this INTR pin is there, hardware pin is there, INTR, or you can call it IRQ. IRQ means interrupt request pin. Okay, is this clear? Interrupt request pin, or you can call it INTR, interrupt request pin. Okay, so these are different names. Now, this was our question. Whenever some device will send interrupt signal to the CPU, how the CPU will decide, how the CPU will know which device has interrupted? This is the first question. The second question is how the CPU will know the address of ISR code that you need to execute? Yes or no? So, very simple. If you want to find out which IO device has sent the interrupt signal, then what you can do, you can use the vectored interrupt concept. Okay, basically the interrupt vector concept you can use. What is this concept? It is very simple. For different vectors, for different interrupt, what we do, we give a unique identification number. See, there are many different type of interrupt. From every IO device, interrupt signal can come, yes or no. So let me tell you, for every different type of interrupt, what we do, we give a unique number, unique identification number for every different type of interrupt. Okay, this unique identification number is called interrupt vector, or you can call it interrupt number, or you can call it interrupt request number. Okay, is this clear? So very simple point, that every type of interrupt in your computer, every IO device basically that will have a unique identification number. Okay, so every interrupt, every type of interrupt will have a unique identification number. This number is a small integer, it is not a big integer, it is a small integer like 0, 1, 2 and so on. This is a small integer. Okay, so this is called interrupt vector. This unique number is called interrupt vector, or you can call it that our interrupts are vectored, means our interrupts are numbered. Okay, basically I can say that we have our interrupts are numbered. Okay, yes or no? Our interrupts are numbered. Okay, to every interrupt we give a unique number, to every interrupt. So this is called vectored interrupt, or you can call it numbered interrupt basically. Okay, so this is the concept. Now what is this interrupt vector? So this is a unique identifier for every interrupt. Each type of interrupt is assigned a unique number. This number is called interrupt number, or you can call it interrupt vector. Now what will happen? See, very simple thing. Let's assume this device, maybe this device is keyboard. Okay, for example, so this keyboard has a device controller, yes or no? Every IO device has a device controller. For example, let's assume this is your keyboard, so keyboard has a device controller. Okay, now what this keyboard device controller will do, let's assume this is sending an interrupt request signal. So this interrupt request signal is coming to the CPU. Now this CPU will now this CPU, what it will do, it will execute the current instruction completely, and then what it will do, it will send the acknowledgement. Okay, so very simple. This device controller is sending the interrupt request to the CPU. The CPU will send acknowledgement signal to the device controller. Now this device controller, what it will do, it will put its interrupt vector, which is a unique number. So this device controller will put its interrupt number on the database, and this number will go to the CPU. Now the CPU knows which IO device has sent the interrupt. Okay, so very simple point. Remember, this CPU has single interrupt request pin and single interrupt acknowledgement pin. Okay, so remember, this interrupt request can come from any device. Yes or no? Any device can send interrupt on this pin. So how the CPU will know which device has sent the interrupt request? Okay, so for that we use the concept of interrupt vector. Means every device has a unique identification number. This is called interrupt vector, or I can say interrupt number. Now what will happen? This CPU, when it will send the acknowledgement, then this device controller, what it will do, it will put the interrupt number or interrupt vector on the databus, and this number will go to the CPU. Now the CPU knows which IO device has sent the interrupt. Okay, now what the CPU will do, now the CPU will check the interrupt vector table in the main memory. Let me tell you, there is an interrupt vector table, IVT. So what the CPU will do, once this interrupt number has come, now the CPU has the interrupt vector. Okay, now the CPU will check the IVT. In the main memory, there is an interrupt vector table. So in this interrupt vector table, this CPU will check that for this interrupt number, what is the address of ISR? Okay, for this interrupt number, what is the address of ISR? Then CPU will execute that ISR. Okay, so this is the simple idea. I hope you understood. So you can see these are the steps. Read this. The device controller will send the interrupt request to the CPU. Now the CPU, what it will do? It will finish the current instruction execution and it will send interrupt acknowledgement. Now what this device controller will do? It will send the interrupt vector, or I can say interrupt number, on the data bus to the CPU. Now the CPU knows which IO device has sent the interrupt. Okay. Now what the CPU will do? CPU will check the interrupt vector table. There is a table in the main memory. There is a table that, okay, for this interrupt number, what is the address of ISR? For this interrupt number, what is the address of ISR? For this interrupt number, what is the address of ISR? So basically in this interrupt vector table, the CPU will find the address of the ISR. Okay, once the CPU will find the address of the ISR, so now CPU has, this is ISR. Let's assume this is your ISR. So now the CPU has the address of ISR. Let's assume address of ISR is 200. So what the CPU will do? Very simple. The CPU will load this 200 in the program counter. Okay, and then CPU will execute this ISR. Very simple. So this is how the CPU will do. I hope it is clear. So we have seen what is interrupt vector table. It is called IVT, or you can call it interrupt descriptor table, IDT. Okay, so what is the idea? That this interrupt vector table, this stores what it does. It stores the address of ISR for each interrupt. For every interrupt, what is the address of interrupt service routine, that is stored in the interrupt vector table. Okay, and this interrupt vector table, remember, this is already present in the main memory. Okay, this interrupt vector table, this is already present in the main memory, and I already told you what will happen whenever the device will send the interrupt signal and the CPU will send the interrupt acknowledgement. Then device itself, read this, device itself will send its interrupt vector number on the data bus to the CPU. And what the CPU will do? CPU will take this interrupt number and it will check in the IVT. In this table, the CPU will check the interrupt number and CPU will find the address of ISR which CPU will execute. Okay. So this is the simple idea. I hope it is clear. Now let's see what is interrupt cycle. This concept also we have seen in the previous lecture. So interrupt cycle, this is a very simple concept that basically what the CPU will do, CPU will execute the instruction, and after executing every instruction, CPU will check for interrupt. Okay, is there any interrupt on the interrupt pin? I told you that CPU has an interrupt pin, yes or no? So this is your CPU. This CPU has this interrupt pin. Let's call it IRQ, interrupt request pin. Okay, there is a interrupt acknowledgement pin also, IACK. Okay, interrupt acknowledgement pin. Also there is an interrupt request pin. Okay, so now notice what will happen, what the CPU will do. CPU will execute the instruction completely because CPU is executing some program, yes or no? Let's assume this is the program that CPU is executing. This is the program. CPU is executing one by one. CPU is executing this instruction, then this instruction, then this instruction. So now what the CPU will do? CPU will execute any instruction, and after executing this instruction, the CPU will check is there any interrupt on the interrupt pin. Basically, the CPU will check is this IRQ equal to 1. Means is there any interrupt present on the interrupt request pin? Is there any interrupt present? If the interrupt is present, then what the CPU will do? Then CPU will jump to the ISR. CPU will execute the interrupt service routine to service the interrupt. Okay, so very simple point. And if the interrupt is not present, if IRQ equal to 0, if there is no interrupt present, then no problem. Then the CPU will execute the next instruction. Okay, so very simple. Remember, after every instruction execution, CPU will check is there any interrupt. If the interrupt is present, then CPU will service that interrupt. If the interrupt is not present, then CPU will execute the next instruction. Okay, so this is the interrupt cycle, or I can say instruction cycle. So in this, you notice one thing, that when interrupts are not disabled, if you allow the interrupts to occur, remember, if interrupts are not disabled, then CPU will check interrupt after execution of every instruction. Okay, after we execute every instruction, so once you execute the instruction completely, you will check is there any interrupt. Okay, so this is the idea. Now one more thing, that remember, we can disable or enable the interrupt. Okay, for example, let's assume you are executing a very important task. Okay, let's assume there is a very important task CPU is executing. So at that time, what CPU can do? CPU can disable the interrupt. Okay, so very simple point, that CPU can disable the interrupt because CPU is executing a very important task. Okay, and then CPU does not want to get disturbed. So if CPU does not want to get disturbed during the execution of this important task, then CPU can disable the interrupt. Okay, so this is the simple idea. Now let's see what will happen. Very simple, that CPU will execute instruction, CPU will fetch the instruction, CPU will execute the instruction. After executing any instruction, CPU, what it will do? If interrupt is disabled, then no problem, then you just execute the next instruction. Yes or no? See, if interrupt is disabled, then what the CPU will do? CPU will just keep executing these instructions. Okay, yes or no? But if interrupt is enabled, then what will happen? If interrupt is enabled, then what will happen? Then after every instruction, CPU will check, is there any interrupt? After every instruction, CPU will check, is there any interrupt? So CPU will check this interrupt pin. Okay, this interrupt request pin, CPU will check, is this equal to 1? If this is equal to 1, then CPU will service that interrupt. Okay, if this is 0, then CPU will face the next instruction. Yes or no? So very simple point. If interrupt is disabled, then CPU will not check for the interrupt, because interrupt is disabled. So CPU will not check for the interrupt, and CPU will keep executing these instructions. But if interrupt is allowed, if interrupt is enabled, then CPU will check for the interrupt after every instruction. Okay, after every instruction, CPU will check, is there any interrupt? Is there any interrupt? Is there any interrupt? Okay, and if there is any interrupt, if IRQ equal to 1, then we will service the interrupt, and then we will run the next instruction. Okay, so very simple point. So this is what I'm saying. When the interrupts are not disabled, when they are not disabled, then the CPU will check for interrupt after execution of every instruction. Okay, and one more thing, remember, interrupt can occur anytime. Okay, when you are executing any instruction, then what will happen? The CPU, what it will do? It will fetch the instruction, it will decode the instruction, it will execute the instruction. So basically, there are many things the CPU will do to execute any single instruction. Let's assume there is an instruction I5. Now, to execute this instruction, CPU, what it will do? CPU will fetch it, CPU will decode it, CPU will execute it. So these things CPU will do. Now remember, during the execution of the instruction, the interrupt can occur anytime. Remember, interrupt can occur here, interrupt can occur here, interrupt can occur here. So interrupt can occur at any time during the execution of the instruction. But CPU will check for interrupt after executing the instruction completely. Okay, at this point, remember, at this point, CPU will check for the interrupt. Okay, so CPU will not check for the interrupt in between the instruction. Okay, is this clear? CPU will not check for the interrupt in middle of the instruction. The interrupt can occur, for example, let's assume interrupt is occurring here during the execution of the instruction. In the middle of the instruction, let's assume interrupt is occurring, but CPU will not check it. CPU will execute the current instruction completely. After executing this instruction completely, CPU will check for the interrupt. Okay, very simple. So this is the idea. Now we have seen what is interrupt processing. Whenever some interrupt will come to the CPU, then what are the steps which CPU will do, which CPU will execute? Yes or no? So that is called interrupt processing. Whenever an interrupt is coming, then what are the steps taken by the CPU? Okay, in a order. What the CPU will do, that is called interrupt processing. Okay, so let's see what the CPU will do. Let's quickly see. So the idea is like this. What CPU is doing? CPU is executing some program, yes or no? So let's assume CPU is executing program, instruction 1, instruction 2, and so on. Now, when CPU is executing this instruction I, then let's assume interrupt has come. Okay, so interrupt is coming when CPU is executing instruction I. Now, what the CPU will do? First, CPU will execute this instruction completely. This instruction I, CPU will execute this instruction completely. Then CPU will send the acknowledgement. Okay, yes or no? So after executing this instruction completely, CPU will check, is there any interrupt? Yes, there is interrupt. So the CPU will send the acknowledgement. The acknowledgement, CPU will send interrupt acknowledgement to the IO device. Now what the IO device will do? Now the IO device will send the interrupt vector. Yes or no? The IO device will send its interrupt number to the CPU. Then CPU will find what the address of ISR. This is the ISR, or I can say interrupt handler. So now the CPU knows the address of ISR. Now remember, before running this ISR, what the CPU is going to do? First, CPU will save this program because CPU is executing this program. Now remember, before running this ISR, what the CPU will do? CPU will save this program, means CPU will save the program counter, because remember, after executing this ISR, the CPU will again resume this execution. So when the CPU will resume this execution, CPU has to start from this instruction. Yes or no? So basically, CPU will save, remember, CPU will save the program counter value. Okay, because CPU need to resume from here. So CPU will save the program counter value. CPU will also save the registers. Okay, CPU will also save the flag register, Because when this program is running, then this program is affecting the flags. There is a flag register, you already know, that is called PSW. Flag register is also called program status word. Okay, this is also basically your flag register. This is the flag register. In the flag register there are many flags. Okay, so when this program is running, then these flags are affected. So this information also we have to save, because when you resume this program, then basically all the information you need related to this program. So very simple point, remember, the CPU before running this ISR, CPU will save this program, or I can say CPU will save the information related to this program, like what is the program counter, what are the register values, what is the program status word, all these things CPU will save. After saving, what the CPU will do? Now CPU has the address of ISR, yes or no? So this address CPU will put in the program counter. Okay, in the program counter CPU will put this address. Then what CPU will do? Then CPU will run this ISR. Okay, very simple. So after putting this ISR address in the program counter, now this CPU will execute this ISR just like a normal program. Okay, CPU is executing this ISR. Now inside this ISR, let me tell you, inside this ISR, maybe some more information CPU can store. Okay, in the stack. Remember, we are storing the information in the stack. For example, the information related to this program also we are storing in the system stack. Okay, in the main memory there is a system stack, or I can say control stack. So remember, the information related to this program we are storing in the system stack or control stack. In the main memory we have a stack section. Okay, so in that CPU is saving the information related to this program. Now remember, when CPU is running this ISR, then some more information CPU can save, or I can say some more information this ISR can save in the stack. Okay, then what we will do? Then we will service the interrupt. Whatever interrupt was there, we will service that interrupt. Okay, after servicing that interrupt, what we will do? What this ISR will do? This ISR will restore this program. Yes or no? Basically, all the information related to this program that we have already stored in the control stack, that we will restore, so that we can resume the execution of this program. So what this ISR will do? This ISR will store the information about this program. Okay, so that we can resume the execution of this program. And then at the end, finally, the ISR is over. After this ISR is over, what will happen? The CPU will resume the execution of this program. So these are the steps which are involved in the interrupt processing. Step by step, I told you. Now let's see. Let's quickly see. These are the steps. These are the general interrupt processing steps. So very simple point. The device controller will send the interrupt request to the CPU. The CPU will finish the execution of the current instruction. After finishing the execution of the current instruction, CPU will check, is there any interrupt? If there is interrupt, then what the CPU will do? CPU will acknowledge the interrupt. CPU will send acknowledgement signal to the IO device. So basically, CPU is acknowledging the interrupt. Now, what the CPU will do? CPU will save the information related to the current program. Okay, the program which CPU is currently running. So CPU will save the information about that program in the stack. Okay, in the stack. So basically, CPU will save program counter value, registers, also program status word. This information CPU will save in the control stack, or I can say system stack. Then what the CPU will do? CPU will load the program counter with the interrupt service routine address. Yes or no? CPU will load the address of ISR in the program counter. Then ISR is running. Okay, is this clear? Now remember, ISR is running. So all these things now are happening inside the ISR. Inside the ISR, what will happen? Let's see. So inside the ISR, remember ISR is a program. ISR is a program. Program means software. Okay, yes or no? So remember, now all these remaining things are happening inside the ISR. Means these are instructions, remember. Okay, all these things are instructions in the ISR. So I can say all these remaining things will be done by the software. Inside the ISR, these things will happen, remember. So these things will be done by the software. And remember, CPU is running the ISR. This ISR is executed by the CPU. So I can say that CPU will execute this program. Okay, now what will happen? Very simple. Inside this ISR, remember, maybe some more information we can save on the stack. Some more information we will save. Then we will service the interrupt. We will process the interrupt request. Then what we will do? Then we will restore the program. Okay, yes or no? The program which we have already saved in the stack, in the control stack, that we will restore. That program we will restore, and then we will resume our program execution. Our program execution will resume. So very simple point. Okay, so you can easily see this diagram, that you can see device controller that will send the interrupt signal to the CPU. What the CPU will do? CPU will finish the execution of the current instruction. After finishing the execution of the current instruction, CPU will check, is there any interrupt? Okay. Now, if there is interrupt, then CPU will send the acknowledgement. Then CPU will save the work or the current work. Yes or no? CPU will save the information related to the current program. So that CPU will save on the control stack, or I can say system stack. Now, after that, CPU will load the program counter with the address of ISR. Then ISR is running. Okay, then remember here, okay, here ISR is running. Inside the ISR, what will happen? We will save some more information on the stack. Then we will process the interrupt. Then we will restore the the interrupted program. Yes or no? We will restore the program which CPU was executing before interrupt came. Okay, so that information we will restore, and then CPU will resume the execution of the interrupted program. So these are the steps. I hope all these steps are clear. So you can read this. We have already seen the interrupt processing steps. Now our topic, that is nested interrupts. Okay, this is our next topic. Let me tell you, so far what I told you, that is the recap of the previous lecture. All these concepts are very important. How to process the interrupt. Okay, what is interrupt service routine? What is interrupt vector? What is vectored interrupt? What is interrupt vector table? Okay, the definition of interrupt. So basically all the concepts that we have seen, we have already seen in the previous lecture in a very detailed way. So this was basically, I can say, the recap of the previous lecture. Okay, is that clear? It so far we have seen the summary of the previous lecture. Now we will study the next topic, that is nested interrupt. This is our next concept, that is nested interrupt. What is nested interrupt? Very simple. When you are executing some interrupt, when I'm servicing some interrupt, means I'm executing the ISR, then also some interrupt can come. Yes or no? Then also some more interrupt can come. So that is called nested interrupt. Means when I'm servicing some interrupt, then also a new interrupt can come. That is called nested interrupt. So let's see the definition of nested interrupt. When I'm servicing some interrupt, when I say servicing interrupt, what that means? Servicing interrupt, what that means? That simply means when I'm executing the ISR. Yes or no? When CPU is executing the ISR, okay, to service the interrupt, the CPU will execute the interrupt service routine. Yes or no? Or I can say interrupt handler. So servicing the interrupt simply means executing the execution of interrupt handler, or I can say execution of ISR. So very simple point. When CPU is servicing some interrupt, then another interrupt can come. Yes or no? So that is called nested interrupt. Nested interrupt simply means that when we are running some ISR, when CPU is executing some ISR, then this ISR can be interrupted by another interrupt. So this is the simple idea. Okay. So let me explain this, the concept of nested interrupt. So you can see that, let's assume CPU is running some program. Okay. This is the program that CPU is running. Okay. Now during the execution of this program, let's assume at this point, some interrupt is coming. Okay. Some interrupt is coming from D0, from the device D0. Okay. This device D0, this can be, for example, mouse, or this can be some other device. So D0 interrupt has come. Interrupt is coming from D0. Okay, device D0 is sending interrupt. So very simple. What the CPU is doing? CPU is executing this program, and at this time, what happens? At this time, you can see the interrupt is coming from device D0. Now, what the CPU will do? CPU will finish the execution of the current instruction, and then CPU will check, is there any interrupt? Yes, there is interrupt. Then CPU, what it will do? It will save the current program. After saving the current program, CPU will jump to the ISR of D0. Yes or no? So what the CPU will do from here? The CPU will execute the ISR of D0. Okay, yes or no? So very simple. The CPU is executing the ISR. This is the ISR. Remember, this is the interrupt service routine for device D0. Okay. Now the CPU is executing this. Now remember, this is also a program. This interrupt service routine, this is also a program. So during the execution of this interrupt service routine, what can happen? Another interrupt can come. Yes or no? Maybe during the execution of this instruction, let's assume that another interrupt has come. Okay, this interrupt has come from device D1. Okay, so this device D1 has sent interrupt at this point. Now what the CPU need to do? That we will see. Basically, you understood the concept of nested interrupt. Yes or no? Now what the CPU will do? Now what the CPU will do, that we need to study. Okay, so let me tell you what are the solutions. Now what the CPU will do? The first solution is very simple. What the CPU will do? At this instruction, interrupt has come from device D1. Then very simple, no problem. So the CPU will just go to the ISR of D1. Yes or no? Is this clear? What the CPU can do? So very simple. During the execution of ISR of D0, at this instruction, let's assume the interrupt of D1 has come, then because this is a normal program, okay, so what the CPU can do? CPU can save this ISR. Okay, again, CPU will execute this instruction completely. After executing this instruction completely, CPU will save this ISR in the stack, in the control stack. Okay, and then CPU will jump to the ISR of D1. Okay, so CPU will jump to the ISR of D1. This is the ISR of D1. Okay, this is the interrupt service routine of D1. Okay, so this is one solution. Is this clear? This is a solution one for nested interrupts. This is solution one for nested interrupts. Tell me, in this solution, is there any problem? Let me know. In this solution, is there any problem? Do you find any problem in this solution? Is there any problem in this solution? This is the solution one for nested interrupts. So yes, there is a problem. What is the problem? See, again, during the execution of this ISR, again some interrupt can come. Again, the CPU will go to the next. Again, some interrupt can come. Yes or no? So basically, there is a problem because a lot of nesting can happen. Yes or no? This is the problem, that you are running some program, some interrupt is coming, you are running that interrupt. Now again, some interrupt is coming, you are running that interrupt. Now again, some interrupt is coming, you are running that interrupt. Okay, yes or no? So basically there is no idea that maybe starvation can happen. Yes or no? It is also possible that starvation can happen. Starvation is possible. Do you agree? Okay, so in this solution, starvation is possible because we have no idea when the CPU will completely execute this ISR. Remember, this is your program. This is your program, but these are ISR. For example, this is ISR1, this is ISR2, this is ISR3. Yes or no? So there is no idea when this ISR will complete. Okay, maybe this is a high priority ISR. Yes or no? Basically, maybe this is a high priority interrupt. This interrupt has very high priority, but still in this method, the problem is, in this method, this high priority interrupt can starve. So starvation possible for this interrupt. Yes or no? Maybe this interrupt is high priority interrupt. Maybe this is high priority interrupt. Okay, yes or no? Maybe this interrupt is high priority interrupt. Now you can see we have no idea when this high priority interrupt will be serviced. Okay, yes or no? So starvation is possible. This is the problem with this approach. So this solution one has the problem of starvation. This solution one, I can say, this has problem of starvation of high priority interrupt possible. Starvation of high priority interrupt possible. Okay, high priority interrupt possible. Interrupt possible. So this is the idea. Okay, is this clear? Please tell me. So did you understand the solution one? See, the concept is very simple. When CPU is executing a program, let's assume some interrupt is coming from device D0. Then what the CPU will do? CPU will save this program and CPU will run the ISR interrupt service routine for D0. But during the execution of this ISR, because this is also a program, this is also sequence of instructions. So during the execution of this ISR, interrupt can come from device D1. Now, now what the CPU will do? That is the question. Now what the CPU will do? This is called nested interrupt. Now what the CPU will do? Then the solution one is the CPU will execute this ISR. Okay, but in this solution, the problem is that any level of nesting can happen. Yes or no? Any level of nesting, because any level of nesting can happen. So starvation is possible for some interrupt service routines. For these interrupt service routines, starvation is possible because we have no idea when this interrupt service routine will complete. Okay, so this is the problem with this solution one. What is the solution two? What is the solution two? What do you think? Anyone? What is the solution two? See, solution two is sequential execution of interrupts. Okay, solution two, what is that? That is sequentially we execute interrupts. Sequential execution of interrupts. Sequential service of interrupts, or I can say execution of interrupts. Okay, in this, what the CPU can do? Basically, this is the idea that CPU, what it will do? CPU will disable the interrupt when some interrupt service routine is running. Okay, is this clear? In this solution two, what the CPU will do? CPU will disable interrupt. Disable interrupt when CPU will disable interrupt when some ISR is running. Okay, so this is the solution to. Solution to is disable interrupt when ISR is running. When some ISR is running, when some interrupt is already being processed. Okay, is this clear? When some interrupt is already being processed, then we disable the interrupt. Okay, so this is the idea. So let me tell you that basically in this solution 2, we will sequentially execute the interrupts. What is the idea? The idea is this. Let's assume CPU is executing this program, and at this point, the device D0 is sending interrupt. Now remember, at this point, CPU is executing the program. So at this point, the interrupts are not disabled. Please understand that solution 2 is saying that we will disable interrupt when some ISR is running, when some interrupt service routine is running, then we will disable the interrupt. Okay, is this clear? Basically our idea is that we will sequentially execute the interrupts. Okay, so the idea is like this, that when this program is running and let's assume this interrupt is coming, then what the CPU will do? CPU will save this program, and after saving this program, CPU will run this ISR. But let me tell you, before running this ISR, the CPU will disable the interrupts. Okay, is this clear? Please tell me, is this point clear? So very simple, that before running this ISR, before jumping to this ISR, CPU will disable, or I can say the hardware will disable the interrupt. Okay, now what will happen? Now when this ISR is running, then we have already disabled the interrupt. The interrupt is already disabled. So what the CPU will do? When the interrupt is disabled, I told you that in this situation, the CPU will not check for the interrupt. Okay, remember interrupt can come. But CPU will not check for the interrupt. I told you. Okay, in the interrupt cycle, I told you in the interrupt cycle that when the interrupt is disabled, then CPU will not check for the interrupt. Interrupt is possible. Yes, interrupt is possible. For example, let's assume some IO device is sending the interrupt. That is possible. But the CPU will not check the interrupt pin. There is an interrupt request pin. CPU will not check that interrupt request pin. Okay, so very simple point. So what the CPU is doing? Before executing this ISR, CPU is disabling the interrupt. So it simply means that after, when the CPU is executing this ISR, during the execution of this ISR, CPU will not check for the interrupt. CPU will execute this instruction, then this instruction, then this instruction. Let's assume when CPU is executing this instruction, let's assume interrupt is coming, but CPU will not check this interrupt because CPU has disabled the interrupt. So CPU will not check for this interrupt. Okay, is this clear? Then CPU will execute this instruction, CPU will execute this instruction. Okay, and then CPU will complete this ISR and CPU will go to the program. Okay, is this clear? After completing this ISR, CPU will go to the program. But let me tell you, one thing will happen. One thing will happen in this ISR, the last instruction. Okay, because when this ISR is complete, then we have to enable the interrupt. Yes or no? Then we should enable the interrupt. So the last instruction of this ISR, that will be what? That is basically enable interrupt. That is enable interrupt. Okay, is this clear? So this is the last instruction. This is the last instruction in this ISR, that you enable the interrupt. Now the CPU, what it will do? It will go to the original program. Okay, now remember one more thing. When the CPU will go to the original program, then it will see, yes, D1 has interrupted. Now the CPU will check the D1 interrupted, because now the interrupts are enabled. Yes or no? Now the interrupts are enabled. So when the CPU will go to this program, okay, CPU will resume this program, then CPU will check, okay, D1 has interrupted. Now the CPU will run the D1. Okay, is this clear? Now the CPU will run D1. Okay, now CPU will run the ISR of D1. Is this clear? So very simple. So you can see in this solution 2, what we are doing, we are disabling the interrupt when ISR is running. So before running any ISR, we will disable the interrupt. And in the ISR, the last instruction will be enable the interrupt. Okay, is this clear? So during the execution of the ISR, if any interrupt is coming, interrupt can come. If any interrupt is coming, then CPU will not check that interrupt. Okay, is this clear? So very simple. Now, so basically here what is happening, that we are sequentially executing the interrupts. Okay, is this clear? Now, is there any problem in this solution? Can anyone find problem in this solution? Anyone, please tell me. Give me one problem in this solution. When ISR is running, we are disabling the interrupt. Okay, so when this ISR is running, we are not checking, the CPU is not checking the interrupt. Is there any problem in this solution? See, the problem is like this, that when CPU is running this ISR, maybe high priority interrupt can come. Yes or no? See, CPU is running this ISR, maybe some very high priority interrupt is coming. Maybe your laptop is about to shut down. Yes or no? Your laptop is about to shut down. Yes or no? So let's assume that some high priority interrupt is coming. Then, then still CPU is not checking this interrupt. Do you agree? So that is the problem in this solution. That in this solution, when the ISR is running, CPU is not checking for interrupt. Maybe very high priority interrupt is coming. Maybe your laptop is about to shut down. So you must save your unsaved work. Whatever your unsaved work, you must save. Yes or no? So that is the point, that in this solution, remember, the problem is that we are not checking, we are not giving basically benefit, or I can say we are not considering the high priority interrupts. Okay, is this clear? So this is the idea, this is the solution too, and I told you the problem, but still this solution is used. Let me tell you, this solution is still used. Okay, why this solution is still used? I told you that, remember, I told you the problem, because maybe during the execution of this ISR, maybe some high priority interrupt can come, but still this solution is sometimes used, not always, but sometimes sometimes we can use this solution. The reason is very simple, because see, this ISR is a very small piece of code. Okay, this ISR, this program is actually very small, very short. It is not a very big program. This ISR, this is a small program. Okay, so it will not take much time to execute. It is a short program. It is a small piece of instruction. So that is the reason. That is the reason this solution is sometimes used. Okay, because this will quickly execute. This ISR is a very small program. It is not a big program. It is a small program, so it will quickly execute. So that is the reason this solution sometimes we can use it. Okay, what is the solution 3? Anyone want to suggest some other solution? Anyone want to suggest some other solution? Yes, a very good solution now I will suggest. What is that? See, the solution is like this. We allow the nested interrupt. We don't disable the interrupt. We allow the nested interrupt. But if high priority interrupt is coming, then we service it. If low priority interrupt is coming, then we don't service it. See, very simple point. Let's assume CPU is executing this program and this interrupt is coming from device D0. Now what the CPU will do? CPU will save this program and CPU will run the ISR for D0. Now remember, when CPU is running this ISR, during the execution of this ISR, if some interrupt is coming, then remember, if this is a high priority interrupt, then D0. Okay, this D1 interrupt, if this is high priority interrupt, then D0, then we will service it. Then we will service it. Okay, is this clear? If this D1, this is a high priority interrupt, then what we will do, if this is high priority, then we will service it. Okay, then we will service it. But let's assume that when you are servicing, when you are running this when you are running this ISR for D1, let's assume another interrupt is coming. Okay, let's assume another interrupt is coming from device D2. Okay, from device D2. Now let's assume that this is not high priority than D1. Means D1 has highest priority. Let's assume D1 has highest priority. Okay, so this is the highest priority, let's assume. So you can see that if this D1 is highest priority, means D2 has low priority than D1, then the CPU will not execute the ISR of D2. Is this clear? So the idea is very simple. When you are running the ISR, when you are running the interrupt service routine, then if higher priority interrupt is coming, higher priority interrupt is coming, then we will service that interrupt. If lower priority interrupt is coming, then we will not service that interrupt. Okay, is this clear? So this is the idea. Now, in this idea, is starvation possible? Anyone want to suggest, in this idea, is starvation possible? Is there starvation possibility in this idea? The starvation possibility is negligible. Okay, what are the reason? Can anyone tell me what are the reason? The starvation possibility is negligible. What are the reason? The reason is because how many higher priority interrupts you can have? Yes or no? Are you getting my point? See, we are only servicing the higher priority interrupt. We are only servicing the higher priority interrupt. Okay, so how many you can have? Maybe 3, 4, 5. Yes or no? So basically, in this solution, let me tell you, this is the useful solution and this is mostly used solution. Okay, so the starvation possibility is negligible. So that is the reason this is the best solution that we use. Okay, is this clear? Let me know. So very simple point. I hope you understood. Now one by one I will discuss all these solutions. Don't worry. I have given you the idea of all the three solutions. There are three solutions for handling the nested interrupts. Yes or no? Our question was how to handle the nested interrupts. For that, we have three solutions. These three solutions we have already seen. Now I will tell you all these three solutions again. Okay, let's see this. But the nested interrupts, did you understand? The nested interrupt concept. What is the nested interrupt concept? Did you understand? The idea is very simple. When you are running the ISR, when you are servicing some interrupt, when you are running ISR, then some more interrupt can come. Yes or no? Then some more interrupt can come. Then some more interrupt can come. This is called nested interrupt. Okay, this thing is called nesting of interrupt. Okay, is this clear? This thing is called nesting of interrupts. So the idea is very simple. You can see when we are servicing the interrupt of device D0, okay, then you can see when a device D0 is interrupted, see, this is the idea. When device D0, when this device D0 is interrupting the CPU, then what the CPU will do? CPU will run the ISR for D0. This you already know. Okay, CPU is running a program. When D0 is interrupting, then CPU will run the ISR of D0. Now, when you are running the ISR of D0, this is ISR of D0. When you are running the ISR of D0, then some interrupt can come. Another device D1 can interrupt. Yes or no? Another device can interrupt. So this is called nesting of interrupts. This is called nesting of interrupts. Now let's see the solutions. So how to handle the nesting of interrupts? So handling nesting of interrupt, there are three solutions. I already told you. Okay, so what are the three solutions? The first solution is simply allow the nesting. Yes or no? Any level of nesting, any type of nesting. Simply allow any type and any level of nesting. Just keep doing nesting, no problem. Okay. But this is not a good solution. So this is not used. Let me tell you this solution. The first solution that we have seen, that is any level of nesting, that is not used. That is not a good solution. Okay, because starvation possibility is there. So that is the reason I can say this solution is not used. This is not a good solution. Another solution is disable the interrupt. Yes or no? Disable any type of nesting of interrupt. This is the solution. Disable any type of nesting of interrupts. So nesting of interrupts we disable. That is another solution. So when some interrupt service routine is running, then we disable the interrupts. Okay, we do not check for the interrupts. So we are disabling any type of nesting of interrupts. This is the second solution. The third solution is like this. The third solution does not disable the interrupt. Okay, so the third solution is like this. What we do, we give priorities to the interrupts. Different interrupts have different priorities. Yes or no? Different interrupts have different importance. Now, only the higher priority interrupt can interrupt the ISR of a lower priority interrupt. So, when lower priority interrupt is running, this ISR of low priority interrupt is running, then the high priority interrupt, if that is coming, then we will service it. So, the idea is very simple. Only high priority interrupt can interrupt the ISR of low priority interrupt. Okay. So let's see one by one. The first solution is simply allow any level of nesting. Okay. So this is not a good solution. We have already seen in this solution the problem we have already seen. So you can see when the CPU is running this program, when the CPU is running this program. So now at this point, what can happen? At this point, let's assume that interrupt is coming. Yes or no? Interrupt from D0 is coming. Then the CPU will save this program. Then CPU, what it will do? It will run this. It will run this ISR. Yes or no? This is the ISR of D0. So CPU is running this ISR. Okay. Now during the execution of this ISR, let's assume another interrupt is coming. Okay, so let's assume that at this point another interrupt is coming, that is a D1. This device D1 has interrupted. Now what the CPU will do? CPU will save this ISR. Okay, CPU will save this whatever is this. So this ISR, this program, CPU will save it. And then what the CPU will do? Then CPU will jump to the ISR of D1. So now the CPU is running the ISR of D1. Okay, so now CPU is running ISR of D1. Now you can see during the execution of this ISR, what can happen? What can happen? Another interrupt can come. Maybe device D2 has interrupted. Okay, now what the CPU will do? CPU will save this ISR. Whatever CPU is doing, CPU will save it in the stack, in the control stack. CPU will save it, and then CPU will jump to the ISR of D2. CPU will jump. CPU will jump to the ISR of D2. ISR of D2. So and so on. Now notice once this D2 is coming, once this D2 is over, once this ISR is over, then what the CPU will do? CPU will restore this from the control stack. CPU will restore this and CPU will resume it. Okay, then when this is finished, then CPU will restore this from the control stack. CPU will restore this and CPU will resume the execution and CPU will complete this. And after completing this ISR, CPU will restore the original program and CPU will resume the execution of the original program. Okay, so you can see we allow any level of nesting. Okay, yes or no? So this is one of the solutions, but this solution is not used. As I told you, this is not a good solution. Why this is not a good solution? Why this is not a good solution? Because starvation possible. Okay, starvation possible. Basically, high priority interrupt can be starved. High priority interrupt can starve. Interrupt can starve. Okay, so this is one of the things. For example, let's assume this is high priority. Let's assume this is high priority. Now if you keep doing nesting, if you keep doing nesting, then we don't know when this will execute. Yes or no? We don't know when this will complete, but this is high priority. Yes or no? This is high priority, but because we allow any level of nesting, any type of nesting, so we don't know when this will complete. Okay, so that is the problem. I hope this point is clear. So this solution is clear. You can easily see you are running the program. In this program, you can easily see that when this interrupt is coming, we will run the ISR. In during this ISR, if interrupt is coming, we will run that. Okay, so like that. So this is your nested interrupt. Okay, any level of nesting. This is any level of nesting. This is not a good solution. Okay. Now let's see the next solution. What that? That is we disable any type of nesting. We disable any type of nesting of interrupt. What this means? This means that before running ISR, we disable the interrupts. Before you jump to the interrupt service routine, what you do? You disable the interrupts so that when you are running the ISR, when I'm running the ISR, then I will not check for the interrupt. Interrupt can come. Remember, IO device can send the interrupt. Okay, no problem. But CPU will not check the interrupt because CPU has disabled the interrupt. Okay, is this clear? So when I am servicing any interrupt, when some interrupt service routine is running, then the CPU will disable the interrupt so that the CPU will run this ISR and then CPU will resume the program execution. So basically, in a sequential way, okay, one by one, in a sequential way, one by one, the interrupts will be processed. Okay, is this clear? So this is the idea. I hope this point is clear. So basically, we will do sequential interrupt processing. Sequentially, one by one, we will do the interrupt processing. What we will do? Before jumping to the ISR, we will disable the interrupt request. Okay, this interrupt request we will disable. So when I'm running the ISR, the CPU will not check for the interrupt. Okay, is this clear? So you can see we will disable the interrupt request when we are servicing the interrupt. Okay, all the interrupts will be processed sequentially. All the interrupts, we will process them one by one. There will be no nesting. We are disabling any level of nesting, any type of nesting we are disabling. Okay, so you can see this diagram. Already this diagram can, you can see that. So CPU is running a program, CPU is running this user program. Now you can see at this point, if interrupt is coming, then you can see CPU will go to this ISR. This is the ISR. But remember, before going to this ISR, CPU will disable interrupt. Okay, CPU will disable interrupt. Now, when this ISR is running, the interrupt can come. Remember, maybe interrupt is coming, maybe interrupt from device Y is coming. Okay, this Y, device Y interrupt is coming. So when this interrupt is coming, then remember CPU will not check this interrupt. What the CPU, because CPU has already disabled the interrupt, so CPU will not check the interrupt and CPU will keep executing these instructions. After this service, this ISR is over, the CPU will go resume the program. But remember, already this interrupt is there. Yes or no? So when the CPU will go to this, when CPU will go to this program, okay, when CPU is going, then we are enabling. Once this ISR is over, then we will enable the interrupt. When this ISR is over, then here, okay, this is the instruction. Here we enable the interrupt. So you can see when the CPU will go to the original program, now the interrupts are enabled. Now the CPU will check, is there any interrupt? Okay, is there any interrupt? Yes, there is interrupt. Yes, there is interrupt. So now the CPU will service this interrupt. Okay, after servicing this interrupt, then CPU will resume the execution. Okay, is this clear? Again, remember, when CPU jumping to this ISR, again CPU will disable the interrupt. Okay, and again here the last instruction is enable the interrupt. Okay, so this is the idea. So you can see we are sequentially executing ISR. This ISR, this ISR, there is no nesting. There is no nesting. So let me make this diagram for clarity, that when this CPU is running this program, this is the program, this is the user program. Okay, so when CPU is running this user program, then let's assume the interrupt is coming at this point, some interrupt is coming, let's assume interrupt from D0 is coming. Then what the CPU will do? CPU will save this program. After saving this program, CPU will jump to the ISR, yes or no? But remember, before jumping to the ISR, this is the ISR, this is the ISR of D0. Okay, so this is the ISR of D0. Okay, so you can see that CPU jumping to this ISR, but remember, before servicing the interrupt, before jumping to the ISR, the CPU, what it will do? It will disable interrupt. It will disable interrupt. CPU will disable the interrupt. Okay, now when this ISR is running, then it is possible some interrupt can come. Yes, it is possible. Yes, it is possible some interrupt can come. Okay, maybe at this point, let's assume this device D1 is sending the interrupt. Okay, so device D1 is sending the interrupt. But remember, the CPU will not check this interrupt. Okay, because interrupt is disabled, so CPU will not check it. Okay, the CPU will execute this ISR completely. Okay, and remember, here the last instruction is enable interrupt. EI means what? This instruction. What is this instruction? Okay. So actually, let me tell you the last instruction. Okay, honestly, the last instruction is return instruction, because we have to return, right? Okay, yes or no? So actually, the last instruction is return instruction. In this ISR, basically there is a return instruction here. The last instruction, because we have to return, yes or no? The last instruction is return instruction. Okay, so normally this is also called RTI, means return from interrupt. Okay, return from interrupt. Return from interrupt. This RTI instruction. The last instruction is basically return instruction. This is also called RTI instruction. Okay, so what is this full form? What is this full form? Full form is return from interrupt. Return from interrupt. Okay, so this is just very simple point, that we have to return from this ISR, yes or no? We have to return to the original program. Okay, so the last instruction is actually RTI, or I can say return instruction. This is return from interrupt instruction. Just before it, we have enable instruction. Okay, enable interrupt. So what is this? What is this? This is your enable. This is the enable interrupt. EI means enable interrupt. So this is the idea. So I hope this point is clear. Very simple. When CPU is running this ISR, before running any ISR, before servicing the interrupt, what the CPU will do? CPU will disable the interrupt. Now, if any interrupt is coming, CPU will not check it. Okay. Now, what the CPU will do? CPU will execute this ISR completely. And here, what the CPU will do? CPU will enable the interrupt. In this ISR, at the end, the CPU will enable the interrupt. Okay. Now you can notice what now the CPU will return, yes or no? Now CPU will return to the original program. CPU is returning. But remember, when the CPU is returning, now the interrupt is enabled, yes or no? When CPU is returning to the original program, now the interrupt is enabled. Okay, so what the CPU will do? CPU will check, is there any interrupt? Yes, there is interrupt from D1. Because there is interrupt from D1, so now the CPU, what it will do? It will jump to ISR of D1. Okay, it will jump to ISR of D1. ISR of D1. Again, the same thing. When CPU jumping to ISR of D1, again the same thing. The CPU will disable the interrupt. Let me call it DI. Let me call it DI. DI means disable interrupt. Let me call it DI. DI means disable interrupt. Okay, is this clear? So disable interrupt. This. So you can see when the CPU jumping to this ISR, then first CPU will disable the interrupt. DI means disabled interrupt. Okay. And again here in this ISR, the last instruction, what is that? That is your EI, means enable interrupt. Okay, yes or no? EI means enable interrupt. Okay, so again the interrupt will be enabled. So this is the idea. I hope this point is clear. So remember, when any interrupt we are servicing, when we are servicing this interrupt, then we will not check for more interrupt. Basically, there is no nesting of interrupt. This is the simple idea. We have no nesting of interrupt. So we will disable any nesting of interrupt. So we are doing the sequential execution of interrupt. We are servicing the interrupts in a sequential way. Okay, one by one. First this, then this, like this. So this is the idea. Okay. So we have seen this. Now, what are the disadvantage of this? Disabling interrupt. What are the disadvantage? What are the drawback? So read the drawback. Drawback is very simple, that when you are running this ISR, see, when I'm running this ISR, now I'm not checking for interrupt. Yes or no? This ISR I am running, now I'm not checking for interrupt. So if any high priority interrupt is coming, a very high priority interrupt is coming, I am not checking it. First I will complete it, then I will service it. Yes or no? So that is a problem. So you can see the drawback, you can read the drawback. The drawback is basically that some high priority interrupt we are not considering. Basically you can see that we are not, see this, we are not taking into account the priority. Okay, yes or no? And we are not considering the time critical needs. Means if some very high priority interrupt is coming, we are not considering it. So that is the problem, that is the drawback. But still this solution is used. I told you this disabling, this disable interrupt, this solution is still used. Okay, what is the reason? The reason is very simple. Because ISR, interrupt service routine, that is a small code, that is a very short, that is not a long code, that is a short code. Okay, so it will quickly be over. Yes or no? ISR, this is a small code, so it will quickly execute. Okay, it will very quickly execute. So this is acceptable solution. Remember this, it disabling, this is a acceptable solution because ISR is very small code. Now what is the third solution? I told you the third solution. The third solution is most used solution. What is that? That is very simple. Basically we will not disable the interrupt. We will not disable the interrupt. What we will do? We will give priority to the interrupts. So different interrupts will have different priority. Now if you are servicing some interrupt, let's assume I am executing the ISR, I am servicing some interrupt. Okay, when I am servicing some interrupt, if higher priority interrupt is coming, if a higher priority interrupt is coming, higher priority, then in this situation what I will do? Then I will do the nesting. So if high priority interrupt is coming, then I will do the nesting, means then I will service this high priority interrupt. But if when I'm servicing, when I'm running this ISR, if lower priority interrupt is coming, then I will not service it. Okay, yes or no? Then I will not service it. So this is the simple idea, that only higher priority interrupts can interrupt the ISR of low priority interrupt. High priority people, high priority interrupt, they can interrupt the ISR of low priority interrupt. So this is the idea. I hope this point is clear. So let's see one example to understand this. Let's assume you have 3 IO devices. Okay, example. Let's consider one example. This interesting example you can consider for understanding. So let's assume we have 3 IO devices. We have 3 IO devices with different priority. Okay, let's assume, for example, you have printer. Okay, and maybe you have disk, and maybe you have some other, for example, maybe keyboard, or maybe disk, or some battery. Okay, so let's assume that this is the battery and there is disk. Okay, so you can easily see, let's assume that priority here, this is the priority is 0, here the priority is 1, here the priority is 2. Okay, is this clear? So these are the priorities. Okay, what is this? This is the priority. So remember, this battery has higher priority, this is the high priority. This 2 means high priority. Okay, let's assume that bigger number is high priority, means this printer has low priority and this battery has high priority. Okay, so we have 3 devices. Is this clear? Now let's see what will happen. Okay, just understand this point. What will happen now? Now let's assume that CPU is executing a user program, correct? Okay, so the CPU is executing this user program. CPU is executing this this is the user program, some program CPU is executing. Some user program. Now let's assume that printer is sending the interrupt signal. Okay, at this point, let's assume that printer is sending the interrupt signal. Okay, yes or no? Correct. Here, printer is sending the interrupt signal. So printer is interrupting here. Okay, now we are running the user program and interrupt comes from printer. Then what the CPU will do? CPU will save this program, and after saving this program, okay, let's assume this is time t equal to 10. Okay, this time you can assume that this is time t equal to 10. So at time t equal to 10, this printer is interrupting. So what the CPU will do? CPU will save this program and CPU will jump to the ISR of printer. Yes or no? So now the CPU will jump to the ISR of printer. This is the Let's assume this is the ISR of printer. This is the ISR of printer. Now, let's assume when this ISR we are executing, let's assume that at this point, let's assume that battery interrupt is coming. Okay, at this point, what is happening? Tell me. At this point, let's assume battery interrupt is coming. That okay, that basically battery interrupt. For example, let's assume you have low battery in your computer. If you have low battery, then the battery controller will send the interrupt to the CPU. Yes or no? So let's assume at this point, when you are executing this printer ISR, okay, at this point, let's assume during this instruction, let's assume battery is sending the interrupt that you have low battery. The system is about to shut down. Connect to charger. Yes or no? So this interrupt is coming to the CPU from the battery controller. Battery controller is sending that, okay, connect to charger, low battery. So this is a high priority interrupt. Yes or no? So now you can see that what we will do, because this is higher priority, this battery interrupt has higher priority than printer. So what we will do, tell me. Then we will go to the battery interrupt. Yes or no? Is this clear? So now we will go to the battery interrupt because battery has high priority. So now we will go to battery ISR, battery interrupt service routine. So now this battery ISR we will execute. Okay, now let's assume when you are executing this battery ISR, for a moment, let's assume that disk is sending the interrupt. Okay, disk is sending the interrupt. Now what will happen? Tell me. Let's assume disk is sending the interrupt. When you are running this battery ISR, the interrupt is coming from disk. Tell me, who has more priority, this battery ISR or the disk? Who has more priority? Battery has more priority. Yes or no? So you can notice we are running a high priority interrupt. So that then we will not service it. Yes or no? This we will not service. Basically, we will not give it service. Okay, yes or no? First, we will complete this. But remember, this interrupt is still there. It's not like we are removing this interrupt. Okay, it is not like that CPU is removing the interrupt. No, this interrupt is still there, but we will not service it. Okay, now after servicing this battery, then what we will do? After servicing this battery, we will go back to this printer ISR. Yes or no? Once this is complete, then what we will do? We will go to this ISR. But remember now something interesting. When you go back to this ISR, then what will happen? Now there is disk interrupt. Yes or no? There is already disk interrupt because disk is already sending the interrupt signal. So disk interrupt is there. So when you go to this printer ISR, when you go back to this instruction, now what will happen? The CPU will go to the disk because disk has more priority. Okay, so from here, remember, before before servicing this printer ISR, before running this printer ISR, the CPU will go and CPU will execute disk ISR because disk has more priority than printer. Okay, so that is the reason the CPU will execute this disk ISR. Then after completing this disk ISR, what the CPU will do? Now the CPU will finish this this printer ISR, and then CPU will resume the user program execution. So is this point clear? So did you notice that what is happening when we are running a program? Basically, when we are running a ISR, when we are servicing any interrupt, then if high priority interrupt is coming, then we will service it. But when you are servicing interrupt, when you are running ISR, if low priority interrupt is coming, then we will not service it. So this is the simple idea. I hope you understood. Let me know. Is this point clear to everyone? You can see in this diagram. Okay, this is a very nice diagram. The CPU is executing the user program. Some interrupt is coming here. Then CPU will go to that ISR. So now CPU is going to printer ISR. CPU is executing printer ISR. Now at this point, let's assume that some more high priority interrupt is coming. Then CPU will service it. Now during this, let's assume some more interrupt is coming, but that is low priority. Okay, means some middle priority. I can say some middle priority interrupt is coming. Let's assume some middle priority interrupt is coming. That is disk. Disk is, let's assume, middle priority interrupt. So this disk interrupt is coming. Then remember, because this has high priority, because this has highest priority, so we will not service this disk interrupt. First, we will finish this, and then what we will do? We will go back to the printer ISR. But because we already have an interrupt from this disk has more priority than printer. So what we will do? Before executing this printer ISR, we will jump to the disk ISR. Then we will finish the disk ISR, and then we will resume the printer ISR, and then we will resume this user program execution. Okay, so this is the complete idea. I hope you understood. So that's it. So this is your nested interrupt. How to handle the nested interrupt we have seen. Please tell me, is everything very clear? Let me know. All the three solutions, are they clear? See, we have seen what is nesting of interrupts. When you are servicing some interrupt, then some more interrupt can come. This is called nesting of interrupts. Yes or no? When I'm running this ISR, then some more interrupt can come. This is called nesting of interrupt. Now, to handle the nesting of interrupt, there are three solutions. The first solution is you just keep doing the nesting. Yes or no? Keep servicing the interrupts. Okay, whenever some interrupt is coming, just service it. Whenever some interrupt is coming, just service it. Just keep servicing the interrupt. Basically, you have any level of nesting. You can do any type, any level of nesting. But that is not good. Yes or no? That is not a good solution, because starvation is possible because you have any level of nesting. Okay, yes or no? Now, there is another solution. The second solution is when I'm servicing some interrupt, then I will disable the interrupt. Means before running the ISR, I will disable the interrupt. CPU will disable the interrupt. Now this ISR will run completely. Okay, and at the end of this ISR, what I will do, I will enable the interrupt. Okay, so very simple. At the end of ISR, I will enable the interrupt. Now I will go to the user program, and then if there is some more interrupt, if there is some more interrupt is there, then what I will do, I will go to that ISR. But remember, before jumping to any ISR, before servicing any interrupt service routine, then what I will do, I will disable the interrupt. So when I'm running the ISR, then I will not check for the interrupt. Interrupt can come, but I will not check it. CPU will not check it because already CPU has disabled the interrupt. So when I'm running the ISR, I will not check for the interrupt. At the end of the ISR, I will enable the interrupt. I will go back to the user program, and then if there is any interrupt, then I will service that interrupt. Okay, so basically we are servicing the interrupts in a sequential way. And the third solution, what is that? That is, I will not disable the interrupt, but what I will do, when I'm servicing some interrupt, and if some high priority interrupt is coming, then I will run that interrupt. Okay, yes or no? I will service that interrupt. Basically, we will service only the higher priority interrupts. Okay, if some ISR I am running and higher priority interrupt is coming, then I will service that higher priority interrupt. But if I am running some high priority interrupt service routine, okay, and let's assume some low priority interrupt is coming, then I will not service it. So this is the simple idea. So these are the three solutions. Are they clear? Let me know. How to handle the nesting of interrupts. The three solutions, are they clear? Now the next concept is multiple interrupts. What is this concept? See, multiple interrupts means if at the same time many devices are sending the interrupt, then what we will do? This is different from nested interrupt. In the nested interrupt, what was happening? In the nested interrupt, when I'm servicing the interrupt, then some interrupt is coming. Yes or no? When we are servicing the interrupt, then some interrupt is coming. This was the nesting. This was the nesting of interrupt. Okay, but now I want to discuss when multiple interrupts are coming at the same time. What this simply means? Okay, when your user program is running, when our user program is running, and then let's assume at this point when I check for interrupt, yes or no? See, after every instruction, let's assume CPU is running instruction I5. After every instruction, CPU will check, is there any interrupt? CPU will check for interrupt. Now if there are many interrupts from multiple devices, okay, from 3 or 4 devices, if interrupts are there, okay, that there are multiple interrupts, now what to do? Now which interrupt to execute? Are you getting my point? So this is the concept that if multiple interrupts are coming at the same time, after execution of every instruction, CPU will check, is there any interrupt? And let's assume multiple devices have sent the interrupt. Now which interrupt to run? Can anyone tell me what should I do? In this type of situation, what is the basic thing? What is your intuition? What should I do? At this point, I check for interrupt, and there are multiple devices are sending the interrupt. There are multiple devices who have already sent the interrupt request. So what should I do? Yes, pick the high priority. Yes or no? So priority mechanism I will use, very simple. This is very common sense, that I will use the priority mechanism. Out of these, I will choose the highest priority. Let's assume this is the highest priority interrupt, so I will run it. This is the simple idea. Okay, so very simple concept, that read this. There are many IO modules. There are many IO devices which are connected to the CPU. Yes or no? So there are many IO modules which can interrupt the CPU. There can be more than one interrupt. There can be more than one interrupt request that can occur simultaneously. Okay, yes or no? Many interrupt requests can occur simultaneously. Now, how to handle multiple interrupt requests that are occurring simultaneously from multiple IO devices? Many IO devices have sent the interrupt request. Now, how to handle? So the idea is very simple. What we will do? We will use the priority. So the priority will come in the picture. Correct? This is the common sense that priority will come into the picture. Basically, what we will do, CPU will service the highest priority interrupt among all the current interrupt request. Yes or no? Let's assume there are four interrupt requests. Okay, at the same time, four interrupt requests are coming from four IO devices. Four interrupt requests are coming. Then CPU will pick the highest among these four. Okay, CPU will pick this highest among these four, and then CPU will service it. Very simple. So this is the idea. So you can see, this is the idea that CPU will service the highest priority interrupt among all the current interrupts. Among all the current interrupt requests, CPU will service the highest priority interrupt. But there is a question. What that? You should ask the next question. That is, how the CPU will know who is highest priority interrupt? How the CPU will find the highest priority interrupt among all the available? This question you should ask. You should think about this question that, see, I know that CPU will service the highest priority interrupt among all the current interrupt request. Okay. But the question is, how the CPU will find how the CPU will find the highest priority interrupt among all the current interrupt request? How the CPU will find? Okay. So that is the question. How the CPU will find the highest priority interrupt among all the interrupt requests that are currently present? So for that, let me tell you, there are two solutions. Okay, there are two solutions. What is the first solution? The first solution is CPU has multiple interrupt lines connected to the CPU in order of priority. This is the first solution. Let me tell you, the solution is like this. See, very simple solution. What we have. So solution number one. Basically, what we want to do, we want to find out among all the current interrupt requests who has the highest priority. Okay, so for that we have the first solution, that is multiple interrupt lines connected to CPU in order of priority. Okay, what I want to say, let me mention it. So this is your CPU. This is your CPU. In this CPU, what we will do, we will make many interrupt pins. Okay, because you can see multiple interrupt pins we will connect to the CPU. There will be many interrupt pins. For example, we will have interrupt pin. This is your interrupt request pin. Remember, this is your interrupt request pin for device 1. Okay, yes or no? There is a device 1. Let's assume there is a device 1. This device 1, for example, this device 1 can be your mouse. Okay, maybe, or maybe this can be your battery. This device 1 can be your battery. So you can see that we have this device 1. There is a dedicated interrupt request for this device 1. Is this clear? There is a dedicated interrupt request line. There is a dedicated pin on the CPU. There is a dedicated pin on the CPU. There is a dedicated pin for this device. Okay, and there is a acknowledgement pin also. Acknowledgement pin also for this device. Okay, so this is the idea. Is this clear? So we have a dedicated interrupt request pin and interrupt acknowledgement pin for this device. Okay, for the next device, maybe the next device D2, that is disk. That is disk. For disk also there is a dedicated pin. There is a dedicated pin for interrupt request INTR2. This is a dedicated request pin for device D2. Okay, is this clear? And there is a acknowledgement pin also, dedicated pin on the CPU for device disk, for this device D2. Okay, and so on. Let's assume the next device, that is D3. Let's assume the next device, that is, for example, maybe printer. Okay, so for this printer also, what we will have? We will have a dedicated interrupt pin. There is a pin on the CPU, INTR pin. There is a dedicated pin on the CPU for this device. And there is an acknowledgement pin also for this device. Okay, is this clear? So you are getting the idea. I hope you are getting the idea. Now, in this, actually, let me tell you that the thing is, these are the order of priorities. Okay, basically, these pins I have connected in the order of priority. This is the priority order of priority. Is this clear? These pins, basically, these IO devices are connected to the CPU by dedicated pins in the order of priority. Is this clear? Let me know. In the order of priority, we are connecting them. Why I am connecting in the order of priority, you might be thinking. You might be thinking, sir, okay, we have pins, okay, that is fine. Maybe we have many pins, that is fine. Okay, but why I'm connecting these devices in order of priority? Can anyone suggest? Can anyone tell me why I'm connecting these devices, all these different IO devices, why I'm connecting them to CPU in the order of priority? Like this is the higher priority, like this is the high priority, this is the low priority. So can anyone suggest why I'm doing this? What is the reason? The reason is very simple. See, when the CPU will see that, okay, there is an interrupt request. Let's assume multiple devices have sent the request. Okay, maybe battery, comma printer, both are sending the request. Means this line is also active, this line is also active. Now what the CPU will do? CPU will not check all the pins. What the CPU will do? CPU will first check this pin. If this pin is activated, then will the CPU check the remaining pins? Just tell me this point, the simple point. See, why I am connecting these devices in the order of priority, let me tell you. Let's assume that this device and this device, both these devices have sent the interrupt request. Means for a moment, let's assume that this is also one. Means okay, let's assume that this is also one, and let's assume this is also one. Means this printer, also the battery, okay, they are sending the interrupt request to the CPU. Now tell me one thing, what the CPU will do? CPU will first check this. CPU will first check this interrupt request pin. CPU will check this pin. If this pin is 1, will the CPU check the remaining? Will the CPU check the remaining? No, CPU will not check the remaining because this is the highest priority. This battery already has the highest priority. So if this INTR1 pin is 1, okay, if this battery has already sent the interrupt request, then CPU will not check these. CPU will just check this and service it. Okay, yes or no? And let's assume this is 0. For a moment, let's assume this is 0. Let's assume this is 0, but these two are 1. Means disk and printer, they are sending the interrupt request. Okay, what the CPU will do? Remember, first CPU will check this pin. If this pin is 0, if this pin is 0, then CPU will check this next pin. If this next pin is 1, then CPU will not check the remaining. CPU will service this interrupt. Okay, is this clear? Please tell me. So this is the solution. I hope you understood the point. See, the question, understand the original question. What was my original question to you? My original question is, let's assume multiple interrupt requests are coming to the CPU at the same time. At the same time, many IO devices are sending the interrupt request. Okay, then priority will come into the picture. What the CPU will do? CPU will run the highest priority interrupt among all the available interrupt requests. That is fine. That is fine. But how the CPU will find the highest priority interrupt among all the current interrupt requests? That is the question. How to find the highest priority interrupt? Okay, for that we have two solutions. The solution one, what is that? The solution one is what you do, you use dedicated interrupt lines connected to CPU for different IO devices in the order of priority. Okay, in this CPU we have multiple interrupt pins, INTR, acknowledgement. Okay, interrupt request, interrupt acknowledgement. For different IO devices, we have different pins on the CPU. Okay, and we are connecting them in the order of priority. Now you can easily see what the CPU will do. CPU will first check the first pin. If the first pin is not activated, then CPU will check the next interrupt request pin. If the next interrupt request pin is not activated, then CPU will check the next interrupt request pin. If the next interrupt request pin is activated, then CPU will not check the remaining. CPU will service it. That is the reason we are connecting the IO devices in the order of priority, so that we don't have to check them. We don't have to check them all. Yes or no? If you randomly connect, then CPU has to check all the pins. Do you agree with me? If you randomly connect all the devices, then CPU has to check all the pins. That is a dumb thing. Because if you randomly connect the IO devices, then in a random order, if you connect the IO devices, then CPU will have to check all the pins to find out the highest priority interrupt. Yes or no? So that is the reason we connect the IO devices in the order of priority, so that the CPU will check the first pin, then second pin, then the next pin, and so on. Okay, if any, for example, let's assume this pin is activated. and these pins are deactivated. So if this pin is activated, CPU will not check the remaining pins and CPU will service the interrupt. So this is the simple idea. I hope you understood. Please tell me, is this point clear? So the why we connect the devices in the order of priority? Is that point clear? But what is the problem in this solution? This solution looks very beautiful, right? Yes, this looks like a good solution, but what is the problem in this solution? Can anyone suggest? There is a very big problem in the solution. What is that? Can anyone suggest? In this solution, what is the problem? It is looking like a decent solution, but it is not used in your personal computer. In my computer, in your computer, it is not used. Nowadays, it is not used. This solution is not used. In the general purpose computer, we don't use this solution. Anyone suggest what is the idea? Why? Because we have many pins on the CPU. Yes or no? CPU has many pins. That is not practically possible. For example, in your computer, let's assume you have 100 IO devices or 1000 IO devices. Then you need 1000 interrupt pins. Yes or no? 1000 pins you need on the CPU. So these many hardware pins on the CPU, that is not practically possible. In our general purpose computer, we don't use this solution. I hope you understood this solution. So let's see this. So our solution one is multiple interrupt lines in the order of priority. For example, you can see this diagram that all the devices, we are connecting them to the CPU. There is dedicated interrupt request pin. There is dedicated interrupt acknowledgement pin for every device. For every device on the CPU, we have multiple interrupt request pin and multiple interrupt acknowledgement pin. Okay, so you can see. And remember, these devices are connected in the order of priority. What it means? It means that this has higher priority than this, and so on. Basically, we are saying, look at this. We are saying that if I is less than j, then then interrupt request I has higher priority than interrupt request j. Basically, I am saying that this line, this interrupt request line has more priority than this interrupt request line. So INTR1 has more priority than INTR2. INTR2 has more priority than INTR3, and so on. So you can see if I is less than j, then INTRI has more priority than INTRJ. So we are connecting these devices in the order of priority. We are using the priority scheme also, and we are connecting the devices in the order of priority. So this was the first solution, but this solution is not a good solution, and you already know why. The drawbacks of this solution is not used. Let me tell you, in our general purpose computer, we don't use this solution. The reason is very simple, because very limited number of IO devices we can connect. Yes or no? In this solution, very limited number of IO devices we can connect on the CPU. Very limited number of IO devices we can connect. Okay, so basically this is impractical to have so many pins. Okay, so many processor pins you need, that is impractical. Okay, so that is the reason we don't use this solution. Okay, so what is the solution now? What is the next solution? The next solution is single. On the CPU, we have single interrupt request and single interrupt acknowledgement. This is the next solution. Okay, so let's see the next solution, that is solution number 2. This solution is practically used. Okay, this is the practical solution. In our general purpose computer, we use this solution. So the solution 2 is single interrupt line. Means on the CPU, remember, on the CPU, we have single interrupt request pin. There is a single pin for interrupt request, and there is a single pin for interrupt acknowledgement. Okay, so this is the idea. Now let me tell you one more thing, that here what will happen. Here the idea is like this, that you have CPU. On the CPU, there is a single interrupt request pin and there is single interrupt acknowledgement pin. So this is our CPU. On CPU, I have single interrupt request pin, INTR. There is INTR and there is INTA. On the CPU, these pins I have single pin for interrupt request and single pin for interrupt acknowledgement. But remember, we have many IO devices. Yes or no? So let's assume you have IO device. For example, this IO device D0 is there. Okay, and maybe this IO device D1 is there. So these are the IO devices. Maybe this IO device D3 is there. So these are the IO devices. Now let me tell you what happens. On the CPU, you have single pin, but remember, these devices have their own pin. Okay, on this device, we have interrupt request pin, also interrupt acknowledgement pin. So let me tell you, these devices have their own INTR pin, interrupt request. So this is the INTR1 pin, and this is ACK pin, ACK1 pin. Okay, so these devices, they have their own pins. For example, okay, this is INTR2 pin, and this is a acknowledgement 2 pin. Okay, so you can see this is INTR3 pin, and this is acknowledgement pin, IACK3 pin. Okay, so these pins are there. But remember, the CPU has only one pin. Then what should I do? Anyone want to suggest how to connect? See, every device has their own interrupt request pin. Every device has on interrupt request pin, on interrupt request pin. But CPU has only one interrupt request and one interrupt acknowledgement. So anyone want to suggest some idea how to connect, how to make this connection, how to make this connection? Anyone want to suggest some idea? The idea is very simple. What we do, we put a OR gate. Okay, there is a big OR gate we put. So this is very simple. This is just a OR gate, right? Okay, this type of OR gate we put. So this type of OR gate we put. Okay, so there is a OR gate we connect like this. This OR gate we connect. Okay, this OR gate we connect, and all these INTR request, all these request pins, all these request pins are connected to this big OR gate. Okay, now you notice what will happen. See, there is a OR gate. This is your OR gate. This is a big OR gate. Correct? Okay, so see what will happen now. All these interrupt request pins, INTR1, INTR2, INTR3, all these interrupt request pins, we connect to the OR gate, and that is connected to the INTR pin of the CPU. Now see, okay, this is very interesting that let's assume these two want to interrupt request. Let's assume this interrupt request and this interrupt request are one. Then what will happen? If any of them is one, then CPU will get the interrupt request. Do you agree? Do you agree? If any of them, means this interrupt request or this interrupt request or this interrupt request, if any of them will have interrupt request, then this INTR will become one. So that is the reason we are putting OR gate. Yes or no? If any of them has interrupt request, then what will happen? Then this CPU will get the INTR signal. The CPU will get the interrupt request. Okay, is this clear? How they are connected? So you can see all these interrupt request pins of the IO devices, they are connected by, they are feeding in the OR gate. We are feeding them in the OR gate, and this is connected to the INTR pin of the CPU. If any of them is activated, means if any of them is asking for interrupt request, then this INTR pin, this will become one. Okay, because this is OR gate. So if any of them is one, then this will become one. Okay, now there is one interesting challenge. What is that? Can anyone tell me? What is the challenge here? There is one challenge. You also might be thinking, what is that challenge? Tell me. In this solution, there is a challenge. What is that? The challenge is like this. The challenge is like this. Let's assume this interrupt request is one. See, just think logically. Let's assume that this interrupt request is one. Okay, this is one. And let's assume this interrupt request is also one. So let's assume these two devices, means this D3, this is also one, and let's assume this is also one. So these two things are one. Okay, this and this, they are one. Now in this situation, what will happen? So basically, this is requesting, remember, this is requesting. This device is requesting interrupt request. This device is requesting. Also, this device is requesting. So these two devices are requesting, but CPU has already one pin. Yes or no? So you can notice this is one, this is zero, this is one. So the OR gate output will be one. So this will become one. Yes or no? Now CPU knows that there is interrupt. Now CPU knows there is interrupt. CPU knows there is interrupt. There is at least one device who is interrupting. Yes or no? There is at least one device interrupting. Do you agree? CPU is thinking that there is at least one device who is interrupting, who needs attention. Okay, there is at least one device who needs attention. So this is what the CPU is thinking, because CPU has only one interrupt request pin. So CPU has only one pin. So that is the reason CPU is thinking that there is at least one device which needs my attention. Which needs my attention. So in this situation, what the CPU will do? What the challenge to the CPU? The challenge is how to find who is the highest priority. Yes or no? How to find, first of all, how to find who is interrupting. Yes or no? At least one device is interrupting, but who is interrupting and who is among them, who is the highest priority? Basically, all the devices who are requesting among them, who is the highest priority? This is the challenge. Did you understand the challenge? Please tell me. Let me know. So you can see the challenge is like this. Read this line. The challenge is how the CPU will find the highest priority interrupt among all the interrupts that are available. How to find the highest priority interrupt? That is the challenge. Okay, so for that, there are two solutions. There are two solutions, let me tell you. The first solution is polling method. The CPU will ask every device, did you interrupt? Did you interrupt? Did you interrupt? I got an interrupt request, but tell me, did you interrupt? Did you interrupt? Did you interrupt? Did you interrupt? So CPU will ask everyone. That is called polling. Do you agree? Okay. See, CPU has single interrupt request. I told you that the CPU has a single interrupt request line. INTR, there is a single line. If the single line is one, now CPU is thinking that at least one device needs my attention. There are many devices, D0, D1, and so on, maybe D100. At least one device needs my attention, but maybe 50 devices need attention. Yes, or maybe 10 devices need attention. So the CPU is thinking, because CPU has only one pin, so CPU is thinking that at least one device needs my attention. But now, how the CPU will find who is the highest among these? Okay, among these, who is the highest? So what the CPU will do? CPU can use the polling method. Polling means CPU will ask, did you interrupt? Did you interrupt? Did you interrupt? Did you interrupt? Okay, for everyone. For everyone, CPU is asking, did you interrupt? And then among all of them, CPU will find who is the highest. So this is, you already understood that this method is not useful. Do you agree? Because CPU is wasting a lot of time. Yes or no? CPU is asking, did you interrupt? Did you interrupt? Did you interrupt? So this method is not a good method because CPU is wasting a lot of time. Okay. So now we use the method number two. The method number one, I told you, in this method number one, the CPU will do the polling. CPU will ask, did you interrupt? Did you interrupt? Did you interrupt? Like this. To every IO device, CPU will ask. Okay. But there is another method, that is daisy chaining arrangement of devices. Okay, that is a clever method. We will see why this is clever. This is called daisy chaining arrangement of the IO devices in the order of priority. Or I can say daisy chaining arrangement for assigning the priorities. This method is also very interesting. Okay, so let's see these two methods one by one. So let's see the first method. What is the first method? We have single interrupt line on the CPU. CPU has a single interrupt request line, single interrupt acknowledgement line. Okay, but we are using polling method to find who interrupted. Okay, did you interrupt? Did you interrupt? So CPU is using the polling method to find who is interrupting. So you can read this here. Basically, CPU will ask, did you request the interrupt? Okay, to everyone, CPU is asking, did you request the interrupt? Did you interrupt? Did you interrupt? So this is just a form of polling. You can see this is just another form of polling. So the disadvantage, you already know the disadvantage, that is in this method. Okay, polling in this method time consuming. This is a time consuming method. So this is not used. Let me tell you. Okay, this is not used. So this method, this polling method, this is not used, or I can say we don't use it. Not used much. Okay, is this clear? So this method we don't use much. But this method number two, this is mostly used. Okay, so let's see what is this method. This daisy chaining method. What this? This is a clever method. This is nothing but a clever arrangement of the devices. That's it. Okay, so mostly used. So this is the idea. Now let's see what is this daisy chaining arrangement. Basically, we will arrange the IO devices in the order of priority, but in a clever way. In a clever way. So let's see what is this daisy chain. So now this is our method number two, that is daisy chaining. You already know that CPU has single interrupt line. CPU has single interrupt request, single interrupt acknowledgement. This is what the CPU has. But what we will do? We will use daisy chaining arrangement of devices in the order of priority. Okay. So let's see what this daisy chaining says. This daisy chaining is like this. See. So let me tell you. This daisy chaining is like this. This is an effective and elegant way. This is a clever way. This is a efficient and elegant way to arrange IO devices physically in the order of priorities. Okay, the IO devices we will arrange physically, we will arrange them in the order of priorities. Or you can say that this method, this daisy chaining method, this is a way to assign priorities to the devices effectively. Okay, now what this means, let's see. So it simply means like this. Do you have CPU? Okay, there is CPU, but CPU has single interrupt request line that you already know. There is a single interrupt request line and there is a single interrupt acknowledgement line, ACK. Okay, this is what the CPU has. But you have many devices. Let me tell you in the daisy chaining what we do. Daisy chaining is like this. The highest priority device we will put here. Okay, we are physically arranging the devices. So this device D0, let's assume this is the device 0. Okay, and this is the highest priority. This is the highest priority interrupt, or I can say highest priority device. So this we will connect. Okay, so first we will connect this basically this we will directly connect to the CPU. Okay, we are going to directly connect to the CPU. This device we will directly connect. Okay, there is device D1. Okay, so this is the order of priority. This is the maximum. Then it has less priority. Then the next device has even more less priority. Okay, so there is device D2. So this device D2, this has the lowest priority. You can think like this, that it has the lowest priority. Okay, so this is how we have connected them. Now let me tell you what will happen. We have a common, because there is a single interrupt request line to the CPU. So this INTR, okay, there is an interrupt request here. This is INTR 0. Yes or no? This is INTR 0. This is INTR 1. This is INTR 2. This is INTR 2. So what we will do? We will connect them by OR gate. Remember, okay, there is a OR gate. We will use the OR gate. So we will use the OR gate. This OR gate we will use. Okay, so like this. And then we will connect them to this. So very simple. So basically there is a single interrupt request line to the CPU. Okay, like this we can connect. Is this clear? Now see what will happen with the acknowledgement. The acknowledgement is like this. We are putting these devices in the order of priority. So that is the reason first I am putting the highest priority, because what will happen? This acknowledgement will first go to this device. This acknowledgement will not go to all the devices. First, this acknowledgement will go to this device D0. Okay. Now this device D0 will be thinking, I did not interrupt. Yes or no? Maybe device D0 did not interrupt. See, if device D0 interrupted, then is there any need of checking the remaining? If device D0 interrupted, is there any need of checking the remaining devices? There is no need. Yes or no? Because device D0 has highest priority. So if this device D0 has interrupted, means if this signal is 1, then you can see there is no need to check these devices. Okay, what will happen? If this device has interrupted, then this device will simply send its address. What this device will do? This device will send its address on the database to the CPU, that okay, I have interrupted. Now this device will send its interrupt number. I told you every device has an interrupt number. So you can see this device will send its interrupt number or interrupt vector on the database to the CPU, and then CPU will execute the ISR for this device. Very simple. Okay, but remember, if this device has not interrupted, means if this signal was 0, then what this device will do? This device D0 will send this signal to the next device. Okay, is this clear? This device D0 will send this acknowledgement signal to the next device. So basically we are propagating this acknowledgement signal. Okay, if this device D0 did not interrupt, if this is 0, then this signal, this acknowledgement signal will go to the next device. Now, if next device has interrupted, then we will not check the remaining devices. What will happen? If this device has interrupted, then very simple, this device will send its interrupt number to the CPU on the database. It will send its interrupt vector to the CPU on the database, and then CPU will execute the ISR. Okay, for device D1, it will execute the ISR of device D1. Very simple. But if this device D1 did not interrupt, then what will happen? Then this acknowledgement will be propagated to the next device. If this device has interrupted, then what will happen? This device will send its interrupt vector, or I can say interrupt number, to the CPU. The CPU will find the interrupt number, and then CPU will find the interrupt ISR address for this device D2. So, and then it will run the ISR for device D2. Okay, so that's it. Very simple. So this is the simple idea. So this is called daisy chaining assignment of priorities. In this method, what happens? If the device is directly connected to the CPU, then it has highest priority. Do you agree? Yes or no? If the device is directly connected to the CPU, if this device is directly connected to the CPU acknowledgement, then this device has a highest priority. Then this will have low priority, then this will have low priority. So this is daisy chaining arrangement of the IO devices in the order of priority. The highest priority device we connect first, then low priority, and so on. This is the order of priority in which we connect the IO devices. So that if this device has requested interrupt, if this device has requested the interrupt, then we will not check the remaining IO devices. Okay, yes or no? So this is the simple idea. This is called daisy chaining assignment of priorities. Because here what is happening? If any device which is connected directly to the CPU, that has highest priority. So very simple. Let me know, did you understand this? So you can see this is daisy chaining arrangement. Okay, in this, these are the order of priorities. So you can easily see that there is a single interrupt request line to the CPU has a single interrupt request line. Remember, there is a OR gate here. Okay, let me tell you, there is a OR gate here. Here we have a OR gate. So very simple, that these devices, they will send their interrupt request to the CPU. Now when the CPU will get interrupt request, now the CPU does not know how many have interrupted. Maybe 10 devices have interrupted. Yes or no? So what the CPU will do? CPU will send the acknowledgement, a single acknowledgement CPU will send. This acknowledgement will go to the highest priority device. Now, if this device has interrupted, then what this device will do? If this device has interrupted, then this acknowledgement signal will not go to the remaining devices. This device will send its interrupt vector, or I can say interrupt number, to the CPU on the data bus. Okay, the CPU will find the interrupt number, and then CPU will find the address of the ISR for device D1, and CPU will execute the ISR for device D1. Very simple. But remember, if this device has not interrupted, okay, then this signal, acknowledgement signal, will be propagated to the next device. Okay, and so on. So if this device has interrupted, then the next devices will not be checked. We will not check them. Okay, this device will send its interrupt number to the CPU, and CPU will run the ISR for device D2. So this is the simple point. So remember, this is a way to assign priorities to the devices. This daisy chaining, this is a way to assign priorities to the devices, because if a device is connected to the CPU directly, or I can say the device that is closer to the CPU, that has higher priority. Okay, is this clear? Any device that is closer to the CPU, that has higher priority. So this is the point. So remember, in daisy chaining, let me write this line. In daisy chaining arrangement, in daisy chaining method, the device which is closer to the CPU has the devices closer to the CPU have higher priorities. The devices closer to the CPU have higher priorities. The same statement you can write in a different way. You can simply say that basically high priority devices are closer to the CPU. Basically, higher priority devices. Okay, high priority devices, or I can say higher priority devices, are closer to the CPU. So this is the point. Okay, so let's move on now. So we have seen what is daisy chaining. Okay, remember, the IO devices are physically ordered by the priority. Read this line. Read this line. The IO devices are physically ordered by the priority. If a device is closer to the CPU, then it has higher priority. Or I can say the higher priority devices, they are closer to the CPU. Okay, and here in this diagram, you can easily see that this CPU has single interrupt request. Yes or no? You can notice. CPU has single interrupt request line, and CPU has single acknowledgement line. There is a single line for acknowledgement, and there is a single line for request. Now you can see these are the IO devices. You can notice that the IO devices are connected like this. See, okay, the interrupt request of all these devices, these are the interrupt request. So you can, in this diagram, actually it will be like this. It will be 2. Okay, it will be 2, it will be 3, it will be 4. Is this clear? So there is a mistake here. This is a typing mistake. So you can see this will be 2. Okay, this is 3, this is 4. So you can see these interrupt request lines, they are feeding in the OR gate. There is a OR gate, and there is a single interrupt request line on the CPU has a single acknowledgement line. Now when the CPU will get the interrupt request, now CPU does not know how many devices have sent the interrupt request, because CPU has a single interrupt request line. Okay, so what the CPU will do, CPU will send the acknowledgement signal. This acknowledgement signal will first go to the this device. Okay, yes or no? This acknowledgement signal will first go to the highest priority device. This is the highest priority device. Okay, so now if this device has interrupted, means if this is one, if this interrupt request one, if this is one, then what will happen? Then this device will send its interrupt number to the CPU on the data bus. Then CPU will execute the ISR for device D1. Okay, but remember, if this device did not interrupt, means if this is 0, then what will happen? This acknowledgement signal will be propagated to the next device. Okay, now this acknowledgement signal will be propagated to the next device. Now the next device, if this next device has interrupted, means if this signal if this interrupt request signal is 1, then this device will send its interrupt number to the CPU on the data bus. Then CPU will run the ISR for this device. Okay, and so on. So one by one. So this is the daisy chaining arrangement. I hope this diagram is clear to everyone. Okay, so in this diagram, actually this should be 2. This should be 2. Okay, in this diagram, this should be 3, and this should be 4. So this is the point. Okay, that's it. Let's move on now. So we have seen this daisy chaining arrangement. Okay, so remember, there is a, you can see the interrupt request line that is common to all the IO devices, because processor has a single interrupt request line, single interrupt request line, single interrupt acknowledgement line. From the processor point of view, remember, single request and single acknowledgement line. Okay, and this is the daisy chaining arrangement. If the device is closer to the CPU, then it has higher priority. Okay, so this is the point. In this daisy chaining, there is a starvation possibility. Do you agree? Okay, because this low priority device, this can starve, because every time what the CPU will do, every time the CPU will first ask this highest priority person, CPU will first ask, do you need service, sir? Okay, if this says I don't need service, then CPU will ask this, okay, do you need service, sir? Yes or no? This acknowledgement will go to the next device, do you need service, sir? Okay, so like this, basically the low priority people, the low priority devices, they can starve. Okay, so that is a problem in this daisy chaining. So you can see this starvation is a problem in this method. So that's it. So we have seen the concepts of interrupt. Now we are going to solve a lot of gate questions from this interrupt. Okay, based on the interrupt concepts, there are many gate questions. Let's solve all of them one by one. So I will ask you all these questions. What you need to do, let me tell you. For every question, you pause the video, you think about the question, you solve the question yourself, and you put your answer in the comments. Then you play the video and you see the solution. This is what you need to do. Okay, for every question, for every gate question, first you pause the video, try to solve yourself. Okay, after solving, whatever answer you get, correct or wrong, doesn't matter. Remember, you should put your answer in the comments, so that when you play the video, and if your answer is correct, it is very good. If your answer is wrong, then also no problem, don't delete your comment. Okay, because you are improving. Okay, your knowledge is improving. So now let's solve. Let's start. Let's solve this GATE Computer Science 1996 question. For the daisy chaining scheme of connecting IO devices, which of the following statement is true? We have already seen daisy chain scheme of connecting IO devices to the CPU. Okay, so which of the following statement is true? Tell me the answer. It gives non-uniform priority to various devices. It gives uniform priority to all devices. It is only useful for connecting slow devices to the processor. It requires a separate interrupt pin for each device. Please tell me what is the correct answer. Let me know. So the correct answer for this question, the correct answer is it gives non-uniform priority to all the devices. So the answer will be option A. See, very simple. In the daisy chaining, what happens? I told you This is an effective and elegant way of connecting IO devices to the CPU. Basically, arrangement of IO devices in the order of priorities. This we have already seen. The IO devices are physically ordered by the priority. Yes or no? In this daisy chaining, what we do, the higher priority device will be connected to the CPU directly. Basically, the devices which are closer to the CPU, they have higher priority. Yes or no? So this is the arrangement of devices in the order of priority. This is higher priority, then this, like this. Okay, very simple. Now you can easily see in this daisy chaining arrangement, this device has more priority, this device has less priority, and so on. This device has lowest priority. Okay, so you can see daisy chaining arrangement gives non-uniform priority to all the devices. Also, one more thing, remember one more thing. Thus, in this arrangement, in this daisy chaining arrangement, there is single interrupt request line on the CPU. There is a single interrupt request line, and there is a single interrupt acknowledgement line. For different devices, we don't have different interrupt request lines. We don't have different acknowledgement lines. Okay, yes or no? So very simple. This is the simple idea. So tell me the answer for this gate 1996 question. That will be it gives non-uniform priority to the various devices, because what we are doing, the device which is connected closer to the CPU, that has higher priority. If this device is closer to the CPU, then this has higher priority in this daisy chaining arrangement. Okay, yes or no? So the option B is wrong, because option B is saying that this will give uniform priority to devices. That is wrong, because if the device is closer to the CPU, then this device will have more priority. Okay. Now, the last statement is also wrong. It requires a separate interrupt pin on the processor. Read this last statement. It requires separate interrupt pin on the processor for each device. This statement is also wrong, because on the processor there is a single interrupt request pin, there is a single interrupt acknowledgement pin. For different devices on the CPU, we don't have different interrupt request pins and different interrupt acknowledgement pin. Okay, yes or no? So this is the idea. Option D is wrong. Option C is saying it is only useful for connecting slow devices to the processor. That is also not correct. Okay, the highest priority device you can connect first, then you can connect the next higher priority, and so on. So you can connect all the IO devices in the order of priority you can connect. Okay, so very simple. For this question, the answer is option A. Let's solve this gate to 2020 question. Option A. In this gate 2020 question, the option A is saying daisy chaining is used to assign priority to the interrupts. Tell me, is this statement correct? We use daisy chaining to assign priorities to the interrupts. Yes, that is correct. Yes or no? Because in this daisy chaining, what happens? If any device is closer to the CPU, if this device is closer to the CPU, then it will have higher priority. So daisy chaining arrangement gives priority to the devices. Okay, in this daisy chaining arrangement, what happens, that this acknowledgement first it will go to this device D1. So that is the reason this device D1 will have higher priority. Okay, yes or no? So very simple, that in this daisy chaining arrangement, we basically, this is a way to give priority to the devices. If a device is closer to the CPU, then it will have more priority. Okay, so for this question, remember, for this question, the daisy chaining is used to assign priorities to the interrupts. This statement is true. Okay, is this clear in this 2020 question? So we have already seen daisy chaining. Let's solve this gate 1995 question. In a vectored interrupt, what will happen? Let me tell you, a similar question has come in ISRO also. In the ISRO also, the question is asking about vectored interrupt or not. Okay, so let's solve both these questions. This gate 1995 question is asking, in a vectored interrupt, what will happen? See, what is the idea of vectored interrupt? Vectored interrupt means that every interrupt has a unique identification number. Every interrupt has a number, unique number. That is called interrupt vector, or that is called interrupt number. Okay. Now, what will happen? Whenever some device is sending interrupt to the CPU, then CPU will send the acknowledgement. This IO device, when it will receive the acknowledgement, it will send its interrupt vector, it will send its interrupt number on the data bus to the CPU. Then CPU will take this interrupt number, and CPU will find the ISR address in the interrupt vector table, and then CPU will run the ISR for this device. This is the complete idea, you already know. Okay, so tell me the answer for this question. In a vectored interrupt, the branch address is assigned to fixed location in memory? No, the answer is option B. Read this option B. This is the answer. In the vectored interrupt, what happens? Read this option B. This is saying the interrupting source, the interrupting device will supply the branch information to the processor through an interrupt vector. That is correct. Option B is correct. Yes or no? We have already seen this. Let's see. In this ISRO question, what is the answer? I will explain, don't worry. In this ISRO question, what will be the answer? An interrupt in which the device will supply the address as well as interrupt request, that is called vectored interrupt. Yes or no? The device is sending the address, the device is sending the unique identification number to the CPU, so that is called vectored interrupt. So for this question, answer is option A. For this ISRO question, answer is option A. And for this gate question, the answer is option B. Okay. Actually, we have already seen the concept of vectored interrupt. The idea is very simple. To every IO device, we give a unique identification number. To every type of interrupt, we give a unique identification number. This is called interrupt vector, or you can call it interrupt number. Okay, so we can call it interrupt number, or we can call it interrupt vector. Now, what happens when this device will send interrupt request to the CPU, then CPU will send acknowledgement to this device. Now this device will put the interrupt number on the data bus. This device is supplying, remember, this device will supply the interrupt vector, or I can say interrupt number, on the data bus to the CPU. CPU will get this interrupt number, then CPU will check interrupt vector table. In the interrupt vector table, CPU will check for this interrupt number, what is the address of ISR, what is the address of interrupt service routine. Then CPU will run the ISR for this device. Okay, so this is the simple idea that we have already seen. These are the steps we already know. The steps are like this. Device controller device controller will send interrupt request to the CPU will finish the execution of the current instruction, and CPU will send the acknowledgement. Now the device controller will send interrupt vector, or I can say interrupt number, on the data bus to the CPU will get this interrupt vector. CPU will check the interrupt vector table. In the interrupt vector table, CPU will find the address of ISR for this device. So CPU will read the interrupt number, and CPU will identify the device. CPU will check the interrupt vector table for address of interrupt service routine for this device. Basically, the interrupt vector that's this CPU is getting, the interrupt number that CPU is getting, for that interrupt number, CPU will check in this interrupt vector table. CPU will check what the address of ISR for this device, and then when the address CPU will get, then CPU will run the ISR for this device. Very simple. So this is the idea. So I hope all these points are clear. So you can notice in the vectored interrupt, what happens? The device itself will send the interrupt vector number on the data bus to the processor. And then processor will check the interrupt vector table to find the address of the ISR to execute. Okay, so remember, for this gate 1995 question, in a vectored interrupt, the option B is correct. The interrupting source will supply the information to the processor through an interrupt vector. So option B is correct. Okay, and for this ISRO question, interrupt an interrupt in which device will supply the address to the processor, that is vectored interrupt. Answer is option A. Now let's move on. Let's solve this gate 2005 question. Which one of the following is true for a CPU having single interrupt request line and single interrupt grant line, means acknowledgement line? Means if your CPU has single interrupt request line, CPU has single INTR pin, or I can say interrupt request pin, and CPU has single interrupt acknowledgement pin, or I can say interrupt grant pin. This is the CPU. Now in this situation, can I say you can only have one IO device? If CPU has single interrupt request pin and single interrupt acknowledgement pin, can I say you can only have one IO device? Can I say you can only have one IO device? No, of course not. Of course not. Yes or no? So you can see vectored interrupts are possible or not? Of course they are possible, no problem. So you can see vectored interrupts are also possible, and multiple interrupting devices are also possible. The answer will be option C. See, if the CPU has single interrupt request pin and single interrupt acknowledgement pin, it does not mean that we can only have one IO device. You can have many IO devices. Okay, yes or no? Also, we can have vectored interrupts, no problem. This we have already seen. Actually, this is the solution that is used in your general purpose computer. Okay, yes or no? We have already seen this, that normally in our computer, in your computer, in my computer, in our general purpose computer, normally the CPU has single interrupt request pin, also single interrupt acknowledgement pin, single pin for interrupt request, single pin for interrupt grant. Okay, and what happens if you have many devices, then you can see that, okay, there is a OR gate here that you already know, yes or no? So the interrupt request from this device, from this device, from this device, the interrupt request will come. There is a OR gate here, there is a OR gate here. So there is a single pin on the CPU for interrupt request. There is a single acknowledgement. Okay, yes or no? And all of them, they can be vectored, no problem. Yes or no? Basically, what will happen? If these devices are sending interrupt request, for example, this device, and this device, they are sending the interrupt request, then what will happen? The CPU will get interrupt request equal to 1. Now CPU will send the acknowledgement. There is a single acknowledgement pin. CPU will send the acknowledgement. If this device has interrupted, then what this device will do? This device will send its interrupt vector to the CPU, and then CPU will run the ISR for this device. So that's it. So you can easily see that if we have single interrupt request line on the CPU, also single acknowledgement line on the CPU, then it does not mean that we can have only one IO device. It does not mean that we cannot have vectored interrupts. Yes or no? We can have vectored interrupts, and we can have multiple IO devices. So option C will be the correct answer for this question. Is this point clear? Let me know. And this is what happens in your general purpose computer. In your computer, in my computer, we only have single interrupt request pin on the CPU. Also, we have single interrupt acknowledgement pin on the CPU. But okay, but we have many IO devices in our computer. Yes or no? Similarly, we have vectored interrupts also. Vectored interrupt simply means that every interrupt has a unique identification number. Every interrupt has a unique interrupt number. Okay, using the unique number, the CPU will check the interrupt vector table, and CPU will find for that interrupt number what the address of interrupt service routine. Then CPU will run that interrupt service routine. Let's solve this gate 1993 question. The details of an interrupt cycle are shown in this figure, and the question is asking that, given that an interrupt arrives every 1 millisecond, what is the percentage of total time that CPU will devote to the main program execution? This is an interesting question, but this is a very, very, very simple question. See this, what the question is asking. The details of interrupt cycles are already shown in the figure. In this figure, already everything is given. Okay, so here in this figure, look at in this figure what we are saying. We are executing the main program. Okay, yes, correct. See, look at this, what we are doing here, till this time we are executing the main program. Okay, the main program we are executing. Then when the interrupt will come, arrival of interrupt, when the interrupt will come, then what we will do? You already know, when the interrupt will come, then what we will do? We will save this main program, we will service the interrupt, then we will restore the main program. Yes or no? Three things will happen that you already know. So you can see, okay, till this moment we are executing the main program. Now when the interrupt will come, then what we will do? First we will save the main program. In saving the main program, 10 microseconds are consumed. Saving the main program, this main program you will save in the stack, in the system stack or in the control stack, you will save this main program. For that, 10 microseconds are consumed. Then we will run the interrupt service routine. We will service the interrupt. Yes or no? ISR we will run. So for that, 80 microseconds are consumed. Then what we will do? Then we will restore the main program, because we want to resume the main program execution. So for restoration of the program, 10 microseconds are consumed. Okay, then again what we are doing? Then again we are running the main program. Okay, yes or no? Here in this diagram everything is given. Here we are again running the main program. So you can see. Okay, so that's it. So this is the main program execution. Now the question is asking that interrupt is coming every 1 millisecond. Okay, every 1 millisecond interrupt is coming. Then what is the percentage of total time that CPU will give to the main program execution? Okay, so let's solve it. See, this question you can solve from 1 second point of view, or you can solve from 1 microsecond point of view. Okay, both Basically, we need to find the percentage of total time that CPU will give to the main program execution. So first, let me tell you that you can solve this question from 1 second point of view, or you can solve this question from 1 microsecond point of view. 1 microsecond. Okay, so within 1 microsecond, what will happen? Let's see. Okay, from 1 microsecond point of view, or I can say, let's solve this question. What will happen within 1 microsecond? Within 1 microsecond. Okay, what will happen? Then after some time, I will tell you another method, that is within 1 second, what will happen? Okay, so you will get the same answer, don't worry. Within 1 microsecond, what is happening? In 1 microsecond, how many interrupts are coming? Can anyone tell me? In 1 microsecond, how many interrupts are coming? Can anyone tell me? Please tell me. In 1 microsecond, okay, so you can see in this 1 microsecond, how, sorry, millisecond. Okay, in this 1 millisecond, how many interrupts are coming? One interrupt is coming, right? Yes or no? Okay, because every 1 millisecond interrupt is coming, that you already know. The question is saying that given that interrupt is arriving every 1 millisecond. Okay, so within 1 millisecond, interrupt is coming. Okay, yes or no? The interrupt will come. Tell me how much time this interrupt will take. How much time this interrupt will consume? You can see interrupt will consume 10 microsecond for saving the main program, 80 microsecond for running the ISR, and 10 microsecond for restoring the main program. So you can see 10 plus 80 plus 10, that is 100 microsecond. Yes or no? So interrupt consumes how much time? Interrupt consumes total 100, that is 10 plus 80 plus 10. So that is total 100 microseconds interrupt will consume. Okay. The remaining time main program will consume. Yes or no? Remaining time for main program execution. Okay. Yes or no? So very simple. Now you tell me how much time, how much percentage we are giving to the interrupt. Tell me percentage for interrupt you can find, then automatically you can find for the program also. So tell me what is the percentage of time consumed by interrupt? Tell me. Consumed by interrupt. Tell me what is the percentage of time consumed by the interrupt? So you can see in 1 millisecond, 100 microsecond is consumed. I want percentage of time which is consumed by interrupt. Yes or no? So you can notice 100 microsecond, 100 microsecond is consumed. Okay, in 1 millisecond, I want percentage. So multiply by 100. What value I will get? Tell me. Micro means 10 to the power minus 6. Milli means 10 to the power minus 3. Okay, so here what will happen? 100 multiplied by 10 to the power minus 6 multiplied by 100 to find the percentage. The question is asking for percentage. You can see percentage. So divided by 10 to the power minus 3. So finally what we are getting? You can see 10 to the power, that will be 10%. Yes or no? You will get 10%. So tell me how much percentage for main program execution? Percentage time for main program execution. For main program execution. Tell me percentage time for main program execution. What is that? That is 90%. Correct? Yes or no? In every 1 millisecond, remember, every 1 millisecond, what will happen? One interrupt will come. When the interrupt will come, then 100 microsecond will be consumed to service the interrupt. Because what we will do, we will save the program 10 microsecond, we will run the interrupt service routine 80 microsecond, then we will restore the program, so 10 microseconds. So you can see that in every 1 millisecond, 100 microseconds are gone for servicing the interrupt. Okay, in the remaining time, we will run the main program. So you can see how much time is consumed for interrupt in 1 millisecond. In 1 millisecond, 100 microsecond is consumed for interrupt. So that is 10%. In 1 millisecond, 100 microsecond that is consumed for interrupt. So you can see percentage of time consumed by interrupt, that is 10%. So main program execution, that is 90%. So for this question, the answer is going to be 90%. Okay, is this clear? Now remember, the same question you can solve from 1 second point of view also. You can solve within 1 second what will happen, that also you can find within 1 second what will happen. Okay, let's see. Maybe this will give you more intuition. So within 1 second, what is happening? See, already the question is saying that read this, the interrupt is coming every 1 millisecond. Okay, the interrupt is coming every 1 millisecond. See, within 1 second, what will happen? Let's assume this is the 1 second. Okay, from here to here, let's assume this is 1 second. This is 1 second. Okay, in this 1 second, you can see what is happening every 1 millisecond. Okay, so this time is 1 millisecond. This is 1 millisecond. So at this time, interrupt will come. At this time, interrupt will come because every 1 millisecond interrupt is coming. Then next millisecond. Okay, next 1 millisecond. In here also, what will happen? Next millisecond. So here also interrupt is coming. Again, interrupt is coming. Okay, so you can see when the interrupt will come, then 100 microsecond will be gone for servicing interrupt. Correct? For servicing interrupt, 100 microsecond will be gone. Okay, very simple. Similarly, for servicing this interrupt also, 100 microsecond gone. Okay, for interrupt to service interrupt. So that's it. So this is the idea. Okay, so you can see every 1 millisecond interrupt is coming. Every 1 millisecond interrupt is coming, and so on. So you just tell me how many times interrupt will come in 1 millisecond? Just tell me how many times interrupt will come, how many interrupts will come, how many interrupts in 1 second, how many interrupts will occur in 1 second. Can anyone tell me? During the period of 1 second, during the period of 1 second, how many interrupts will occur? Let me know. That is very simple. Here interrupt is occurring, first interrupt, then second interrupt, then third interrupt. So you can see every 1 millisecond interrupt is occurring. So how many interrupts will occur in 1 second? That is 1 second divided by 1 millisecond, because every 1 millisecond interrupt is coming. Remember, every 1 millisecond interrupt is coming. It's like this. It's like this, that in 1 millisecond, in 1 millisecond, one interrupt is coming. Okay, in 1 millisecond, one interrupt is coming. So in 1 second, how many? That will be 1 divided by milli. These many interrupts will occur. Okay, and what is that? Milli, that simply means 10 to the power minus 3. So that will be 1 divided by 10 to the power minus 3. These many interrupts will occur. That is 1000 interrupts will occur. Okay, is this clear? So in 1 second, remember, in 1 second, 1000 interrupts are occurring. So that's it. So you can see total 1000 interrupts will occur. Is this clear? In 1 second, 1000 interrupts are occurring. So tell me, in 1 second already, we have seen that in 1 second, 1000 interrupts. So tell me how much percentage time is consumed for interrupt. So you can see within 1 second, 1000 interrupts, 10 to the power 3 interrupts occur. Okay. So tell me, what is the percentage of time consumed for interrupt servicing in 1 second? What is the percentage of time consumed for interrupt servicing? Consumed by interrupt servicing. So that will be what? 1000 interrupts are already coming, remember. So every interrupt is consuming 100 microsecond, yes or no? See, there are these many interrupts multiplied by every interrupt is taking 100 microsecond divided by in 1 second multiplied by 100, because we want to find the percentage. Correct? So what is that value? That value again will be 10%. Okay. This value you can check. This is again 10%. Is this clear? So you can easily see. So percentage of time consumed for interrupt servicing per second, okay, 10%. Okay, in 1 second, within 1 second, this is happening. So you can see 10% time is consumed for interrupt servicing. So tell me, what is the percentage of time consumed for main program execution? Percentage of time for main program execution. Main program execution. What is that? That is 90%. Okay, remaining time we are executing the main program. So the answer will be 90%. Please tell me, did you understand this question? Let me know. Okay, very simple question. Every data is already given to you. You can see here main program. Okay, till this point, please notice, till this point main program is executing. From here also main program is executing. In between 100 microsecond for servicing the interrupt. Now this question is actually very easy. You can easily solve it. Okay, so that's it. We have seen the gate questions from this interrupt topic. Okay, now for revision sake, can you quickly tell me the answer of these questions? All these questions I found in a standard book. So let's quickly answer. Let's quickly, because we have already seen all these concepts. Okay, answer the following questions. In the interview, if someone asks you these questions, then can you answer? How can the CPU identify the interrupting device? Quickly tell me the answer. How can the CPU identify the interrupting device? What will happen? Very simple. Every interrupting device has a unique identification number that is called interrupt vector. Yes or no? Every type of interrupt has a interrupt number, unique identification number, that is interrupt number or interrupt vector. Now, so you can see, you with the help of interrupt vector, the CPU can identify the interrupting device. Okay, what will happen? When the device will send the interrupt request, then CPU will send the interrupt acknowledgement. Now the device will send its interrupt number to the CPU on the data bus. Now the CPU has the interrupt number of this device. So with the help of that interrupt number, CPU can find out that, okay, which device is interrupting. Okay, so you can see how to find which device is interrupting. The answer is using interrupt vector. Okay, now the next question is, how can the CPU obtain the starting address of appropriate ISR? How can the CPU will obtain the starting address of interrupt service routine? This is also very simple. What will happen? When any device will send the interrupt request, CPU will send the interrupt acknowledgement. Now this device will send its interrupt number on the data bus to the CPU. Now the CPU has the interrupt number. Yes or no? CPU has the interrupt number. Now the CPU will check the interrupt vector table. In the main memory, there is an interrupt vector table. There is a IVT interrupt vector table. In this interrupt vector table, CPU will check for this interrupt number, what is the address of ISR. So here the CPU will find the address of the ISR, and then CPU will run the ISR. Okay, so very simple. So this is the idea. I hope this point is clear. So you can see how the CPU will find the address of ISR. That is very simple, using interrupt vector table and using interrupt vector. This interrupt vector, who will supply this interrupt vector? This will be supplied by the device itself. The device which is sending the interrupt request, that device will send the interrupt vector to the CPU. Okay, very simple. Now, what is the answer for the next question? How the interrupt nesting is handled? There are three ways. We have already seen there are three solutions for handling the interrupt nesting. The first solution is, you just keep allowing the nesting, means any level of nesting, any type of nesting, you just allow. Okay, keep allowing the nesting. So the another solution is, disable the interrupts when you are jumping to the ISR. When you are servicing some interrupt, then before servicing the interrupt, you disable the interrupt. And after servicing the interrupt, you enable the interrupt. Okay, so basically, the second solution is disable the interrupt before jumping to the ISR. Or I can say that we are sequentially executing the interrupts. Now, the another solution is, what we can do, we do not disable the interrupt. What we do, if some ISR is running, if I'm servicing some interrupt and higher priority interrupt is coming, then I will run it. But if I'm servicing the interrupt and lower priority interrupt is coming, then I will not service it. Okay, so these are the solutions for handling the nested interrupts. So how to handle the nesting of interrupts? There are two. You can see these are the solutions which we use in our computer. That is, either we disable the interrupt, or we allow high priority interrupt to be nested. How should two or more simultaneous interrupt requests be handled? Tell me. If multiple devices are simultaneously sending the interrupt request, the CPU is getting interrupt request simultaneously from multiple devices, then how the CPU will know who is the higher priority interrupt? Okay, so how to handle multiple requests simultaneously? Very simple. What we will do, we will use the concept of priority and we will use the concept of daisy chaining. Yes or no? We will connect the IO devices physically in the order of priority to the CPU. The IO device which is closer to the CPU has higher priority. Okay, so this method, this daisy chaining method, we have already seen. So priority mechanism using daisy chaining method, this is the answer for this question. So that's it. This is your chapter. I hope you understood. Please tell me, did you understand everything in a very crystal clear way? Can you visualize all the concepts? If someone asks you nested interrupt, how many solutions are there? There are three solutions. Okay, what disable interrupt means? What what is multiple interrupts at the same time? If many interrupts are coming, then how to handle? What is daisy chaining method? Okay, so basically all the concepts. Please tell me, are they crystal clear in this interrupt? There are many questions in the GATE exam. We have already done all the questions based on interrupts which have come in the GATE exam. Okay, so please tell me, did you understand all these concepts in a very crystal clear way? A very small topic is remaining, that is types of interrupts. This is a very small topic. This is not a big topic. We need to study the type of interrupt like hardware interrupt, software interrupt, maskable interrupt, non-maskable interrupt. Okay, so some type of interrupts we will study in the next lecture. This is a small topic. This is not a big topic. Okay. So you can find all the lectures on interrupts or IO organization or computer architecture. You can find on the YouTube. You can just search Go Classes COA. Okay, on the YouTube, Go Classes COA means computer organization and architecture. So here you will find computer organization architecture. Okay, this playlist you will find. Okay, you can check it out in this playlist. Inside this playlist, you can see these lectures are there. You can see IO organization lecture 1, where we are discussing what are IO devices, what is IO interface, what is memory mapped IO, what is isolated IO. This is the lecture 2 for IO organization, that is we are discussing programmed IO and interrupt driven IO. And this is the lecture 3 where we are discussing interrupts and interrupt processing. And this current lecture, that is lecture 4. Okay, so in the current lecture we are discussing how to handle the nested interrupts, how to handle the multiple interrupts. Okay, so this was our lecture 4. In this we have done the gate PYQs based on the concept of interrupt. Okay, so I hope you understood everything. Please let me know if there is any doubt. Let me know in the comments. Also please like and please share your feedback in the comments. Okay, thank you everyone.